There is a place in the depths of space where it seems the universe itself is staring back at us. A colossal, luminous structure known as the Helix Nebula, a sight so profound it has earned the nickname the Eye of God. From our vantage point, this vast cosmic eye, with its intricate rings of glowing gas, appears serene, almost peaceful, but this serenity is a beautiful illusion. Peer closer into that brilliant core, into the very pupil of this celestial eye, and you will find a chaotic and violent frontier, a place where the normal rules of physics are stretched to their breaking point, and where mysteries pile upon mysteries in a dazzling display of cosmic strangeness. This is not a static painting in the sky. It is a dynamic, evolving crime scene on an unimaginable scale, the final, dramatic act in the life of a star. And the secrets it holds are far more bizarre than we ever could have imagined. What we are looking at is a planetary nebula, the final farewell of a sun-like star. Located about 700 light-years away in the constellation Aquarius, this is the ghost of a star, the luminous shroud of gas blasted into space as the star exhausted its nuclear fuel. But to call it simply a shell of gas is to miss the entire point. The Helix Nebula is a cosmic onion, and with each layer we peel back, we uncover another set of perplexing oddities that challenge our fundamental understanding of how stars live and die. The questions begin to multiply the moment we focus our most powerful telescopes on its heart. Why does its structure appear so impossibly complex? What forces are sculpting those delicate, comet-shaped knots of gas that swarm like bees around the central white dwarf? Are we witnessing something unique, or is this a preview of our own sun's distant future? Today, we are going to journey directly into the core of this nebula to uncover 40 of its most compelling and peculiar secrets. This will be a tour of cosmic anomalies, from unexplained energetic outbursts and mysterious dust formations to the potential for bizarre chemistry that should not exist. We will explore the fate of planets that may have survived the star's death throes and question if the very geometry of space-time is being warped in ways we are only beginning to comprehend. This is more than a list of facts. It is an expedition into the unknown, a deep dive into a realm where every answer seems to generate two new, more profound questions. So prepare to have your perception of the cosmos reshaped as we unravel the enigmas hidden within the glowing heart of the Helix Nebula. Our journey into the heart of the Helix Nebula begins appropriately at the very source of all this cosmic splendor. The central star, a white dwarf, is the faded remnant of the star that once was, but calling it faded is a serious misnomer. This stellar corpse is an engine of incredible power. With a surface temperature soaring to over 120,000 degrees Celsius, it is nearly 20 times hotter than our own sun. It is this ferocious heat that pumps out immense amounts of ultraviolet radiation, which in turn slams into the expelled layers of gas, causing them to fluoresce with that characteristic ethereal glow. The entire nebula is essentially a cosmic neon sign, and the white dwarf is the electric current that brings it to life. Yet the star itself presents a profound puzzle. How did a star that was once so similar to our sun become this incredibly dense, Earth-sized cinder, spinning with such ferocious energy? The process of its death was both violent and intricate. After swelling into a red giant and blowing off its outer layers, all that remained was its incredibly dense core, a ball of degenerate matter where a teaspoonful would weigh several tons here on Earth. But the details of this transformation are not fully understood. The star's current mass, its rotation speed, and its exact composition are critical pieces of a puzzle we are still assembling. Getting these details right is essential because the behavior of this white dwarf dictates the entire life cycle and ultimate destiny of the nebula that surrounds it. It is the puppet master, and the glowing gases are its dancing marionettes. This leads us to one of the most pressing questions about its eventual fate. A white dwarf like this has two possible paths forward. It can simply cool down over tens of billions of years, fading into a cold, dark black dwarf, a hypothetical end state for stars like this. Or if it has a binary companion from which it can pull material, it can be pushed over a critical mass limit, triggering a cataclysmic supernova explosion. Determining which path this particular star is on is a major focus of astronomical research. The answer doesn't just tell us about this one object, it gives us a preview of what will happen to our own solar system in the far, far future. Understanding this mysterious central star is the absolute key to decoding every other oddity we are about to encounter in the Helix Nebula. But if the central star is the engine of this cosmic display, then the shape of the nebula itself is the stunning signature of that engine's hidden workings. The Helix Nebula presents us with our second and perhaps most visually striking oddity. From a distance, it appears as a nearly perfect glowing ring. This is the classic view, the one that earns it the Eye of God moniker. However, this spherical illusion is just that, an illusion created by our perspective. When astronomers mapped its structure in 3 dimensions, they made a startling discovery. The Helix Nebula is not a simple bubble. It is actually a double-lobed or bipolar structure. Imagine 2 vast, opposing hourglasses or balloons extending outwards from the central star in opposite directions, with the ring we see being the thick equator of this complex shape. This double-lobed form is a critical clue telling us that the star's death was anything but a simple, symmetrical explosion. A spherical star should, in theory, die a spherical death, puffing out its atmosphere evenly in all directions. The presence of these 2 distinct lobes screams that something intervened, that a powerful force funneled the dying star's material into these specific polar outflows. So, what could create such a dramatic channeling effect? Astronomers have 2 leading suspects, and both point to dynamics far more complex than a star dying alone. The first and most compelling suspect is a binary companion. Imagine the central star in its red giant phase having a smaller stellar partner orbiting closely. As the giant star swelled, its companion would have been engulfed in a superheated atmosphere, creating a cosmic dance of incredible violence. The gravitational tug of war between the 2 stars, combined with their orbital motion, would have acted like a powerful pump, focusing and accelerating the outflow of gas primarily along the rotational axis of the system, literally squeezing the nebula into its bipolar shape. The companion star would be the sculptor, carving the nebula's grand design with its gravitational chisel. The second suspect is immense magnetic fields. A dying star can generate extraordinarily powerful magnetic fields. These fields, much like the iron filings aligning around a bar magnet, can constrain and direct the ionized gas being ejected. Instead of expanding freely, the gas is forced to flow along the magnetic field lines, which often stream out from the star's poles. This would create the very same bipolar lobes we observe. It's even possible that both a binary companion and intense magnetism worked in concert, creating a feedback loop of forces that resulted in this uniquely beautiful and intricate structure. This double-lobed shape forces us to abandon the idea of a peaceful stellar demise. It is evidence of a violent, directed, and highly organized cosmic event, a final act shaped by powerful, unseen forces. Yet for all the grandeur of its overall bipolar shape, the Helix Nebula holds an even more intricate secret, one that becomes visible only when we zoom in with the sharpest eyes of our telescopes. Scattered throughout the inner regions of the nebula, particularly along that famous glowing ring, are not just wisps of gas but thousands of distinct finger-like structures. These are the Cometary knots, and they form our third and perhaps most visually arresting oddity. Each knot is a colossal cloud of relatively cool, dense molecular gas and dust, and they are arranged with an almost eerie uniformity, all pointing their heads directly toward the central white dwarf like a fleet of spaceships frozen in formation. They are not small features. Each one is roughly the size of our entire solar system, with a bright, condensed head and a long, faintly glowing tail streaming away from the star. The name Cometary knot is a perfect description of their appearance, as they look strikingly like giant comets. But these are not icy bodies from the outer solar system. They are the surviving fragments of the star's original atmosphere, the last remnants of its outer layers that did not get blown away completely during the initial violent expulsion. They are the mountain peaks of a dying world, the densest parts of the nebula that have managed to hold themselves together against the onslaught of radiation from their ferocious parent star. Their heads are bright because that is where the gas is most concentrated, and it is fluorescing intensely under the ultraviolet barrage. The tails are the material that is being steadily boiled away and eroded by that same stellar wind, creating a wake that stretches across trillions of miles of space. The existence of these knots raises a fundamental question. How did such orderly structures form from what should have been a chaotic explosion? A star shedding its atmosphere might be expected to create a smooth, if turbulent, cloud. Instead, we see this vast collection of individual, organized entities. Astronomers have developed several compelling theories to explain this phenomenon, and they all revolve around the delicate interplay between different types of material and the immense energy pouring from the center. One leading theory involves a process called instabilities. As the hot, fast wind from the white dwarf slams into the slower-moving, cooler shell of gas that was ejected earlier, the boundary between them becomes unstable. Think of it like blowing a steady stream of air across the surface of a thick milkshake through a straw. The smooth surface of the shake doesn't stay smooth for long. It begins to ripple and form peaks and troughs. In the nebula, these ripples can amplify, causing the cooler shell to fragment into countless dense clumps, the seeds of the cometary knots. The pressure from the stellar wind then shapes each clump, compressing the side facing the star to form a bright head and stretching the opposite side out into a long, streaming tail. Another fascinating explanation points to a shadowing effect. Imagine the nebula is filled with dense, dusty blobs from the very beginning. These blobs cast long shadows behind them, shielding the gas in their shadow from the star's intense ultraviolet radiation. Gas that is not irradiated remains cooler and denser, while the gas around the shadow gets heated up and evaporates away. Over time, this process effectively sculpts the surrounding material, accentuating the original blob and creating the classic head-tail structure we observe. It's a cosmic game of preservation through shadow, where being hidden from the light is what allows a structure to survive. What makes these knots so scientifically valuable is that they are temporary. The same radiation that makes them glow is also slowly destroying them. Estimates suggest they may only survive for another several thousand years, a blink of an eye in cosmic time, before they are completely evaporated and dispersed into the surrounding nebula. This gives us a precious, time-limited window to study the processes of molecular cloud survival and destruction in an extreme environment. They are like natural laboratories, showing us how structures form and die under pressures and energies we could never hope to replicate on Earth. Their very presence tells a story of both creation and destruction happening simultaneously on a truly epic scale. Now, as we examine these cometary knots more closely, we uncover a secret hidden deep within their dense, cold hearts. While their glowing outer layers are superheated by the central star's radiation, the cores of these knots are surprisingly frigid, acting as deep freeze units on a cosmic scale. It is within these shielded, icy interiors that astronomers have made one of the most startling discoveries associated with the Helix Nebula: the presence of water ice and a rich inventory of complex organic molecules. This finding transforms our understanding of these structures from mere beautiful curiosities into potential cradles for the very chemistry that leads to life. Imagine the environment inside one of these knots. The outer surface, facing the white dwarf, is blisteringly hot, but just a short distance inward, The thick cocoon of gas and dust provides such effective insulation that temperatures plummet to only a few tens of degrees above absolute zero. In this deep freeze, atoms and simple molecules floating in from the surrounding nebula can stick together on tiny dust grains, forming icy mantles. It's a process similar to frost forming on a cold window pane, but playing out over trillions of miles. Within these ices, shielded from the destructive ultraviolet radiation, a quiet cosmic chemistry lab is at work. Simple molecules link up to form more complex compounds, including polycyclic aromatic hydrocarbons, sooty, carbon-based molecules that are considered fundamental building blocks of life. This revelation leads us to a profound and almost paradoxical idea. We typically think of a planetary nebula as a place of utter destruction, the violent end of a world. Yet, here we see that within the aftermath of that destruction, in the very shadows of a dead star, conditions can arise that are remarkably hospitable for the formation of life's ingredients. Each cometary knot, in a sense, becomes a miniature solar system in the making. It possesses a central density of material, a varied temperature gradient from its hot head to its cold tail, and a rich molecular soup. While these knots will not last long enough to form planets, they demonstrate that the fundamental processes of molecular complexity can occur in the most unlikely of places. The presence of these ices and organics forces us to reconsider the journey of the elements. The star that died to create the Helix Nebula was a nuclear forge, creating carbon, oxygen, and nitrogen in its core throughout its life and during its death throes. When it expelled its outer layers, it seeded the surrounding space with these essential elements. Now we see that these elements aren't just scattered randomly, they are being gathered, organized, and processed within these knots. When the knots eventually evaporate, they will release this enriched material back into the interstellar medium, where it may one day become part of new stars, new planets, and perhaps new life. The Helix Nebula, therefore, is not just a tomb, it is also a nursery, contributing its own legacy of complex chemistry to the ongoing cycle of galactic evolution. This oddity connects the death of one star to the potential birth of life elsewhere, making the cosmos feel both more destructive and more creative than we ever imagined. The sheer scale of the Helix Nebula is difficult to grasp, but its growth is even more staggering. This cosmic structure isn't just hanging motionless in space, it is exploding outward at a breathtaking velocity. The gases in that iconic ring are racing away from the central star at speeds approaching 30 kilometers per second. To put that into perspective, that's over 100,000 kilometers per hour, a pace that would allow you to travel from Earth to the Moon in under 15 seconds. This isn't a slow, gentle inflation. It's a violent, ongoing expansion that defines the nebula's very existence. This incredible speed provides us with a cosmic clock. By measuring the expansion rate and knowing the distance to the nebula, about 700 light-years, we can perform a remarkable calculation. We can work backward to determine just how long ago the central star began its final act. The math points to a surprisingly recent event, astronomically speaking. The cataclysm that created this magnificent sight likely occurred only around 10,000 years ago, a mere moment in the history of the universe. This means that when the earliest human civilizations were first developing agriculture and building their first settlements, the light from this stellar death was just beginning its long journey across the void toward Earth. What's truly mind-bending is that we can actually perceive this expansion from our vantage point, not in real time, but through precise measurements over time. While it would take centuries for the change to be noticeable to the naked eye through a telescope, sophisticated astronomical instruments can detect the nebula's subtle increase in size over just a few years. This observable growth drives home a crucial point. The beautiful planetary nebula phase is extraordinarily fleeting. Within the next 10,000 years or so, the expanding gases will have become so thin and diffuse that they will simply fade from view, blending invisibly into the interstellar medium. The brilliant eye of God will slowly close, leaving behind only the faint, hot white dwarf to mark its passing. This rapid expansion also helps explain the presence of the cometary knots we discussed earlier. The sheer force of the outward blast is what helps create the instabilities that fragment the shell of gas into those distinct structures, but it also seals their fate. The same expansion that formed them is also carrying them further into the vacuum of space, while the relentless radiation from the central star continuously erodes them. The entire nebula is in a state of dynamic tension, a brief, glorious bloom between the violence of its birth and the quiet dissolution of its future. This oddity reminds us that cosmic beauty is often a temporary phenomenon, a flash of brilliance in the dark that underscores the constant, dramatic change happening all across the universe. Moving inward from the grand architecture of the nebula and its sprawling cometary knots, we encounter a more subtle yet equally fascinating layer of complexity. The mesmerizing patterns of light and shadow within the helix are not random. They are a direct map of an ongoing battle between light and matter. These intricate textures are created by what astronomers call ionization fronts, and they form our sixth profound oddity. An ionization front is essentially a cosmic shoreline, a constantly shifting boundary where the tide of intense ultraviolet radiation from the central white dwarf crashes into the cold, neutral gas of the nebula. At this boundary, the radiation is so powerful that it strips electrons from the atoms in the gas, transforming them into a glowing, ionized plasma. This process is what gives the nebula its brilliant luminosity, but it doesn't happen uniformly. The radiation carves its way through the nebula at a speed dictated by the density of the gas it encounters. Denser regions resist ionization longer, creating shadowed pillars and dark lanes, while less dense areas light up almost instantly, forming bright, expansive cavities. The entire nebula is a dynamic, three-dimensional light show, with these fronts sculpting the gas in real time. This interplay creates a stunning visual fossil record. The intricate pattern of glowing ridges and dark, dusty globules is not a snapshot of a single moment, but a layered history book. Each ripple and indentation in the ionization front corresponds to a specific event in the star's final 1,000 years. As the dying star pulsed and shuddered, ejecting its atmosphere in fits and starts rather than a single smooth outflow, it created shells of gas with slightly different densities. When the final, intense ultraviolet flash from the newly formed white dwarf began to illuminate this complex structure, it did so sequentially. The radiation encountered the most recent, least dense ejector first, ionizing it rapidly and creating the large, bright inner cavities. Then it began to eat into the older, denser shells ejected earlier in the star's death throes. The dark knots and filaments we see are the remnants of these older, more resistant mass loss episodes, now being slowly eroded and exposed by the stellar radiation. By carefully studying the geometry and position of these ionization fronts, astronomers can literally unwind the clock, reconstructing the timing, strength, and even the direction of the stellar winds that shaped this cosmic masterpiece. It's as if the star's final gasps were recorded in the glowing gas, waiting for us to decode them. But to truly appreciate the light show playing out across the nebula, we must look beyond the broad brushstrokes of its shape and focus on the intricate chemical details written into its very fabric. As we shift our attention to the specific elements glowing within the gas, we encounter our seventh compelling oddity: vast, intricate filaments that shine with an unexpected and intense signature of oxygen. This isn't just a trace amount. Certain regions of the Helix Nebula are remarkably rich in this element, glowing far brighter in the specific wavelengths of ionized oxygen than we might predict. This overabundance is a direct message from the grave, a forensic clue about the final moments of nuclear fusion that took place deep within the star's core before its catastrophic demise. To understand why this is so significant, we need to think about the life cycle of a star like the one that created the helix. For billions of years, it powered itself by fusing hydrogen into helium in its core, much like our Sun does today. This is a stable, long-lasting process. However, as the hydrogen fuel runs low, the star undergoes a dramatic transformation. It swells into a red giant, and its core contracts and grows hotter, eventually reaching temperatures high enough to begin fusing the accumulated helium into carbon and oxygen. This helium burning phase is far more turbulent and shorter-lived than the hydrogen burning era. The star doesn't burn this fuel evenly. It can experience violent pulses and flashes, shaking the entire stellar structure. The key to the oxygen-rich filaments lies in the precise details of this final act. The fusion of helium is a delicate balancing act. Under most conditions, the process creates primarily carbon. But if the core becomes hot enough and the fusion rates run exceptionally high, a second helium nucleus can be slammed into a carbon nucleus before it can escape, creating oxygen. The presence of these oxygen-rich pockets in the Helix Nebula strongly suggests that in its final 1,000 years, the star experienced a period of extremely intense and efficient helium burning. This episode was so powerful that it tipped the scales, favoring the production of oxygen over carbon. When the star subsequently ejected its outer layers, it didn't just spew out a uniform mix of elements. It flung out shells of gas that had been processed differently at various depths, with the oxygen-enhanced material from these intense burning phases now visible as distinct luminous filaments. This makes the nebula a spectacular chemical map. By carefully analyzing the distribution and intensity of the oxygen glow, astronomers can essentially perform an autopsy on the star. They can determine not just what the star's final fuel was, but how violently it burned that fuel. The intricate patterns of these filaments trace the convection currents and mixing processes that were churning the star's interior right up to its death. It's as if we are looking at a snapshot of the star's internal engine, frozen in time and then blown up to a cosmic scale for us to study. This oddity transforms the helix from a beautiful object into a crucial data set, providing direct evidence for the complex and sometimes unstable nuclear processes that govern the final years of Sun-like stars. While the brilliant glow of oxygen tells a story of intense, deep-seated fusion, a different element provides an equally dramatic yet contrasting narrative. Scattered throughout the Helix Nebula, interwoven with the oxygen-rich filaments, are prominent regions that shine with the distinct signature of ionized nitrogen. This nitrogen anomaly presents a compelling puzzle because its distribution is not random. It often appears in shells and arcs that are physically separate from the brightest oxygen zones. This clear chemical separation is a direct and powerful clue, revealing that the nebula is not a homogenized cloud but a layered relic, preserving the onion-like structure of the original star itself. The star did not die in a single, smooth eruption. It shed its skin in distinct episodes, and each layer we see today was forged under different conditions at a different depth within the stellar interior. To understand the significance of this nitrogen, we need to journey back in time to the star's earlier life. Nitrogen is not a primary product of the core fusion processes that create elements like oxygen and carbon. Instead, it is largely manufactured in a separate region of the star called the hydrogen-burning shell, a layer just outside the core where hydrogen is still being fused into helium. This process, known as the carbon-nitrogen-oxygen cycle, does create some energy, but its most important consequence is that it transforms carbon and oxygen into nitrogen. The material in this shell becomes enriched with this specific element over millions of years. When the star began its death throes, the violent convective currents churning through its vast interior brought this nitrogen-rich material from the hydrogen-burning shell up to the surface, where it was eventually ejected into space. The key to the anomaly lies in the timing of these ejections. The oxygen we see was forged deep in the core during the star's final, frantic helium-burning phases and was likely expelled in a last violent pulse. The nitrogen-rich material, however, probably comes from an earlier, more gentle mass loss event. Imagine the star as it first entered its red giant phase. Its outer layers became so extended and weakly bound that a steady stellar wind began to carry them away. This initial wind would have been composed primarily of material from the star's outer envelope, the very region that had been processed by the hydrogen-burning shell and was therefore rich in nitrogen. It was only later, during the more catastrophic final act, that the deeper, oxygen-enhanced layers were blasted outwards. The fact that these two elemental signatures remain somewhat distinct today, rather than being completely mixed, indicates that the expulsion events were separated in time and had different energies. The nitrogen-rich gas had already expanded to a significant distance when the oxygen-rich material came rushing out behind it. This stratification turns the Helix Nebula into a three-dimensional geological cross-section of a star. By meticulously mapping the locations of nitrogen versus oxygen, astronomers can literally peel back the layers of the corpse to understand the sequence of its demise. The outer, more diffuse regions, which may be richer in nitrogen, represent the star's first, slower size. The inner, brighter filaments glowing with oxygen are the evidence of its final, explosive death rattle. This oddity provides an unprecedented window into the internal structure and mass loss history of intermediate mass stars, offering a level of detail that computer models alone could never achieve. It shows us that a star's death is not a simple event but a complex, multi-stage symphony of expulsion, with each movement leaving its own unique chemical signature on the expanding cosmic canvas. This layered chemical history, with its distinct shells of nitrogen and oxygen, hints at a deeper structural secret within the dying star, a hidden scaffold that ultimately dictated the grand design of the entire nebula. To understand how a spherical star could produce such a distinctly bipolar shape, we must look for an invisible constraint, a cosmic mold that channeled the explosion. This brings us to our ninth oddity, the theorized presence of a dense, dusty torus encircling the central star. A torus is essentially a donut-shaped ring, and in the case of the helix, this isn't a small piece of jewelry. It's a colossal structure, likely trillions of miles across, composed of gas and immense quantities of microscopic dust grains. This torus is the missing piece of the puzzle, the key that may explain the iconic double-lobed structure we see today. The concept is both elegant and powerful. Imagine the star in its final millennia, shedding material in a series of slow, massive winds. During this phase before the final cataclysm, it's possible that the star's own rotation or the gravitational influence of a binary companion caused it to eject far more material from its equator than from its poles. Over time, this would have built up a thick, slow-moving belt of gas and dust girdling the star's middle. Later, when the star's core experienced its final, violent outburst, the resulting fast-moving wind slammed into this pre-existing equatorial belt. The dense torus acted like a set of cosmic earmuffs, presenting an almost impenetrable barrier along the star's equator. Unable to expand freely in that direction, the energetic outflow from the dying star was forced to find the path of least resistance, bursting out through the less obstructed polar regions above and below the torus. This process effectively funneled the explosion, sculpting the two vast, opposing lobes that characterize the Helix Nebula. The challenge, and what makes this oddity so compelling, is that we cannot see this torus directly in visible light. It is composed of cool, dark dust that absorbs the brilliant visible and ultraviolet radiation from the central star rather than reflecting it. Its presence must be inferred, like a detective building a case on circumstantial evidence. The primary clue is the nebula's very geometry. The fact that we see two clear lobes with a pinched waist strongly points to a physical obstruction in the equatorial plane. Furthermore, when astronomers turn their instruments to the infrared part of the spectrum, the case becomes much stronger. Cool dust glows brightly in infrared light, and observations from space telescopes have revealed a distinct excess of infrared emission precisely from the central region of the nebula, aligned with its equatorial plane. This is the thermal signature of the warm dust in the torus, heated gently by the central star. By analyzing this infrared glow, scientists can estimate the torus's composition, temperature, and total mass, revealing it to be a substantial structure containing a significant fraction of the material the star ejected. This hidden torus does more than just solve a morphological mystery. It connects the Helix Nebula to a broader family of cosmic phenomena. Similar dusty tori are believed to play a crucial role in shaping many bipolar planetary nebulae, and on a much grander scale, they are a fundamental component of active galactic nuclei, where they feed and obscure supermassive black holes. The presence of such a structure in the helix demonstrates that these shaping mechanisms are a universal process, occurring across an incredible range of scales. The torus, though hidden from our direct view, is the master architect behind the nebula's beautiful form, a silent testament to the complex and dynamic forces that govern even a star's final moments. But the story of the Helix Nebula's expansion is not one of uniform speed. Nestled within the overall, rapid outward flow of the main nebula, astronomers have detected something far more extreme: narrow, high-velocity outflows. These are not gentle breezes, they are cosmic bullets, jets, and fast-moving clumps of gas screaming through space at speeds that can exceed 150 kilometers per second. This is our 10th profound oddity, a phenomenon that points to an even more violent and concentrated energy source at the very heart of this system. While the general expansion of the nebula tells the story of the star's outer layers being blasted away, these high-speed jets are the signature of a secondary, far more focused cataclysm. The existence of these outflows forces us to confront a critical question: what could possibly accelerate gas to such incredible velocities long after the main explosive event? The central white dwarf, for all its ferocious heat, emits radiation that pushes on the gas, but it doesn't typically create such narrow, collimated jets. Radiation pressure is more like a steady, omnidirectional shove. To achieve the needle-like precision and raw speed of these outflows, you need a different kind of engine, one that can channel and focus an immense amount of energy. Astronomers have two primary suspects for this cosmic particle accelerator, and both imply a dynamic environment far more complex than a single dying star. The first and perhaps most compelling suspect is a hidden binary companion. Imagine the scene: the central white dwarf has a smaller, denser partner, such as another white dwarf or a main sequence star locked in a tight orbital dance. As these two stars whirl around each other, the intense gravitational field can act as a powerful slingshot. If the primary white dwarf is still actively pulling material from its companion, a process known as accretion, this stolen gas doesn't just fall onto the surface quietly. Instead, it can be focused and launched away from the system's poles by powerful magnetic fields and centrifugal forces, creating the very jets we observe. In this scenario, the Helix Nebula is not just a relic of a past death. It is a system that remains active, with a second chapter of stellar interaction still being written. The second suspect points to dramatic events on the surface of the white dwarf itself. While these stellar embers are generally stable, they are not always peaceful. A white dwarf can experience enormous thermonuclear explosions on its surface if it accumulates a critical layer of hydrogen from the interstellar medium or a companion. These bursts, known as nova, are capable of ejecting shells of material at tremendous speeds. It is possible that the high-velocity clumps we see are the shrapnel from such a nova explosion that occurred sometime after the main nebula was formed. Alternatively, the white dwarf's own magnetic field, which can be billions of times stronger than Earth's, might be capable of launching material in a manner similar to the solar flares from our Sun, but on a vastly more powerful and catastrophic scale. What makes these high-speed outflows so scientifically valuable is that they act as probes, slicing through the slower-moving nebula material. As they travel, they interact with the surrounding gas, creating shock waves that heat the material and produce specific, detectable wavelengths of light. By studying these interactions, astronomers can learn about the density and composition of the regions the jets are passing through, much like how a sonar pulse maps the ocean floor. Furthermore, the direction and alignment of these jets provide a crucial clue to the rotational axis of the entire central system. They are like arrows pointing to the hidden engine's orientation, revealing the fundamental geometry that governs the dynamics at the heart of the nebula. Their presence confirms that the drama at the center of the helix is far from over, and that the legacy of this star's death includes ongoing, high-energy events that continue to shape its cosmic aftermath. So far, the story of the Helix Nebula has been written in light, the brilliant visible glow of ionized gases, and the fierce ultraviolet radiation that powers it. But to uncover its next layer of secrets, we need to shift our vision to a part of the spectrum invisible to our eyes. When we point infrared telescopes toward the helix, the nebula transforms completely. The familiar glowing eye vanishes, replaced by a radiant halo of heat. This is our 11th oddity, the profound infrared glow that reveals a hidden universe of cool dust, a component that contains more total mass than the entire visible nebula and tells a completely different chapter of the star's life story. This dust isn't the fine, powdery substance we might picture. It's a cloud of microscopic solid particles like fine sand or soot, but on a cosmic scale. These tiny grains are the unsung heroes of the nebula's formation. They form in the relatively cool, extended atmosphere of a red giant star, where atoms of elements like carbon and silicon can stick together and form solid clusters. The infrared glow we detect is the thermal radiation from these grains, warmed by the faint but persistent heat of the central white dwarf. Their distribution is a stunning revelation. While the visible gas forms the iconic bipolar lobes, the infrared dust often outlines a massive toroidal structure, a thick donut-shaped ring encircling the central star, confirming the presence of the theorized equatorial torus that helped shape the entire nebula. This dust map provides the physical evidence for the invisible scaffold that guided the star's final explosion. The composition of this dust is a direct fingerprint of the star's chemical nature in its final millennia. Most stars, like the one that created the helix, are oxygen-rich, meaning there are more oxygen atoms than carbon atoms in their atmospheres. In such an environment, the dust that forms is primarily composed of silicates, essentially grains of sand and rock, similar to what you'd find on a beach. However, if a star is carbon-rich, the dust will be composed of graphite and more complex carbon compounds resembling soot. Detailed spectroscopic analysis of the helix's infrared light shows a strong signature of silicate grains. This tells us that during its red giant phase, this star remained an oxygen-rich entity. This single piece of data helps rule out certain evolutionary paths and confirms that the star's internal nuclear processes followed a particular sequence, ultimately determining the very type of solid matter that would seed the surrounding interstellar space long after the star itself had died. The sheer quantity of this dust is equally telling. The total mass locked up in these tiny particles is staggering, likely containing a significant fraction of all the heavy elements the star manufactured over its lifetime. This tells a story of a slow, purposeful shedding of material, not just a sudden catastrophe. The majority of this dust could not have formed in the violent final expulsion. It had to be created during the long, steady wind that characterized the star's red giant phase. Over tens of thousands of years, the star gently blew its atmosphere into space, and in the cool, spacious outer layers of that expanding envelope, atoms had the time and conditions to condense into solid form. The presence of so much dust indicates a prolonged and fertile period of mass loss, a final act of cosmic recycling where the star meticulously packaged its elemental legacy into solid form before the grand finale. This dusty shroud is the preserved memory of the star's quiet, billion-year-long final sigh. Yet for all the brilliance of the ionized gases and the hidden warmth of the dust, there is a third, more subtle light shining within the Helix Nebula, a light that signals one of its most profound contradictions. When astronomers trained their instruments on the specific wavelengths emitted by molecular hydrogen, they were met with an unexpectedly intense glow, especially from within the Cometary knots. This is our 12th oddity, and it presents a serious puzzle. Molecular hydrogen, which is simply two hydrogen atoms bound together, is the most basic molecule in the universe, but it is also incredibly fragile. In an environment like the core of the helix, which is flooded with the central white dwarf's devastating ultraviolet radiation, these delicate molecules should be torn apart in an instant. The fact that they not only survive but actually thrive, emitting their own distinct light, points to a set of remarkably specialized conditions hiding in plain sight. The survival of this molecular hydrogen hinges on a fascinating concept known as self-shielding. Imagine one of the massive Cometary knots, a trillion-mile-wide cloud of gas and dust. Its outer surface, facing the white dwarf, is indeed a violent inferno where molecules cannot form. But just beneath this blistering surface, the density of the gas increases dramatically. This dense interior acts like a cosmic radiation shield. The ultraviolet photons, which are so effective at breaking molecules apart, find their energy gradually absorbed by the very first layers of hydrogen atoms they encounter. By the time the radiation penetrates deeper into the knot, its most destructive power has been sapped. In the cold, dark, and heavily protected core of the knot, the conditions are perfect for hydrogen atoms to gently bump into one another and stick together, forming stable molecules. It's a bit like finding a lush, green oasis deep inside a sun-scorched desert. The harsh external environment creates the very shelter that allows life to persist within. But simply surviving isn't enough to explain the glow we detect. For the molecular hydrogen to emit light, it has to be energized. This is where a two-step dance of destruction and creation comes into play. The same ultraviolet light that threatens to destroy the molecules is also responsible for making them shine. When a UV photon with just the right amount of energy is absorbed by a hydrogen molecule, it doesn't always break the bond. Instead, it can push the molecule into an excited, vibrating state. A fraction of a second later, the molecule relaxes back to its calm state, releasing that excess energy as a photon of infrared light. This process, known as fluorescent emission, turns each cometary knot into an intricate lamp. The knot's outer layers sacrifice themselves, absorbing the deadly radiation, which in turn creates a softer, internal light show from the protected molecules within. The entire structure is a perfect balance of violence and preservation. This molecular hydrogen emission is far more than a pretty light. It is an invaluable diagnostic tool. The specific wavelengths and intensities of the light emitted act as a cosmic thermometer and barometer for the knots. By analyzing this fluorescent signature, astronomers can peer deep into regions that are otherwise completely opaque. They can determine the temperature, density, and even the pressure inside these cosmic incubators with incredible precision. This data reveals that the interiors of the knots are astonishingly cold, often only a few tens of degrees above absolute zero. This confirmation of a deep freeze environment supports the idea that these knots are ideal factories for the formation of more complex ices and organic molecules, providing the stable, cold conditions necessary for delicate chemical bonds to form. The glow of molecular hydrogen, therefore, is the beacon that guides us to the hidden, chemically rich hearts of the Helix Nebula's most enigmatic structures. While the visible and infrared light paint a vivid picture of structure and chemistry, a more penetrating form of energy reveals a hidden layer of violence at the heart of the helix. When X-ray telescopes like NASA Chandra Observatory turned their gaze toward the nebula, they detected a faint but definite glow of high-energy X-rays emanating from the central region. This discovery marks our 13th profound oddity because the presence of this specific radiation was both unexpected and difficult to explain. X-rays are the signature of matter heated to millions of degrees, a temperature far exceeding the already scorching 120,000-degree surface of the white dwarf itself. So, what incredible process is superheating gas to such an extreme in this supposedly aging system? Astronomers have been investigating two primary theories, and the debate hinges on whether the central star is a lonely widow or still locked in a dynamic partnership. The first and more straightforward explanation involves a colossal collision. Picture the fast, thin wind currently blowing from the white dwarf, a stream of particles racing outward at several thousand kilometers per second. This wind doesn't travel through a vacuum. It's slamming into the slower-moving, denser shell of gas that was ejected earlier in the star's death throes. The point where these two winds meet is a sight of unbelievable violence. It's akin to a sonic boom in air, but on a cosmic scale, creating a powerful shock wave that compresses and heats the gas to temperatures in the range of millions of degrees. Gas this hot naturally emits X-rays. In this scenario, the X-ray glow is the result of a continuous, high-speed traffic accident occurring throughout the inner nebula, a permanent shock front generated by the persistent wind of the dead star. However, the second theory is far more intriguing and points to a hidden complexity. What if the X-rays are not coming from a diffuse shock front, but from a much more concentrated and energetic source? This possibility suggests the presence of an accretion disk, a swirling, superheated whirlpool of gas funneling onto the surface of the white dwarf from an unseen binary companion. In this model, the white dwarf's immense gravity strips material from its partner star. This stolen gas doesn't fall directly inward. It spirals around the star, forming a disk that becomes intensely heated through friction and gravitational compression. The inner regions of such a disk can easily reach the multi-million-degree temperatures required to produce the observed X-rays. This would mean the Helix system is not a solitary object but an active binary, where mass transfer is still ongoing, powering a high-energy engine at its core. Distinguishing between these two models is a major challenge in modern astrophysics. The key lies in the precise location and distribution of the X-ray emission. If the shock front theory is correct, the X-rays should appear as a somewhat extended, diffuse glow permeating the inner cavity of the nebula, tracing the vast boundaries where the winds collide. If, however, the emission comes from an accretion disk, it should be pinpointed exactly on the central star system itself, a compact and brilliant beacon of high-energy light. Current observations have not yet provided a definitive answer. The signal is faint, and the resolution of X-ray telescopes makes it difficult to distinguish between a slightly extended source and a truly point-like one. This ambiguity is what keeps the mystery alive and compelling. The implications of each possibility are profound. If the shock front model is correct, it tells us that even a lone white dwarf can generate high-energy phenomena through its interaction with its own past, creating a natural laboratory for studying extreme plasma physics. But if an accretion disk is the true source, it revolutionizes our understanding of the system. It would provide the long-sought-after evidence for a binary central engine, neatly explaining not only the X-rays but also the bipolar shape of the nebula and the potential origin of the high-velocity jets. It would mean the drama at the heart of the Helix is ongoing, a second act of stellar interaction that continues to unfold millions of years after the star's initial death. This X-ray mystery, therefore, is not a minor detail. It is a crucial piece of the puzzle that could ultimately reveal the fundamental nature of the entire system. Now we come to a force that is utterly invisible, yet may hold the master key to the nebula's intricate architecture: magnetism. When astronomers search for the fingerprints of magnetic fields within the helix, they find a pattern that defies simple explanation. Instead of the neat, orderly field lines you might expect from a symmetrically expanding shell, the data suggests a web of magnetic fields that are tangled, patchy, and strikingly asymmetric. This is our 14th oddity, a hidden framework of force that could be the invisible hand sculpting the gas and dust into the breathtaking forms we observe. To grasp why this is so significant, think of a magnetic field as a cosmic guidance system for charged particles. In the searing hot plasma of the nebula, where atoms have been stripped of their electrons, the resulting ions are highly susceptible to magnetic influence. These fields don't create the structures from nothing. Rather, they act as a director on a cosmic stage, channeling the flow of ionized gas, reinforcing certain shapes and suppressing others. A uniform, spherical magnetic field would lead to a simple, bubble-like expansion. But the complex, lopsided fields we detect in the helix provide a perfect explanation for why the reality is so much more elaborate. They can stabilize the delicate cometary knots against disintegration, help focus the high-velocity jets into narrow beams, and enhance the instability processes that fragment the expanding shell in the first place. The question then becomes, where did these messy magnetic fields come from? They are almost certainly a magnified legacy of the original star's own magnetism. As a star like the Sun evolves and then dies, its magnetic field doesn't just vanish. During the red giant phase, as the star swells to a colossal size, its magnetic field is stretched and woven into its hugely expanded atmosphere. When this vast envelope is finally ejected, the magnetic fields frozen within the gas are carried outward into space, like invisible threads woven into a tapestry. But they aren't ejected smoothly. The star's final death throes are turbulent, involving pulses of mass loss and powerful winds that tangle and amplify these primordial fields, creating the complex and asymmetric structure we detect today. It's a fossil magnetic field, a ghostly impression of the star's final, chaotic moments, now imprinted on the nebula at a truly monumental scale. What's truly fascinating is the potential for a feedback loop between the magnetic fields and the very dust we discussed earlier. Dust grains, especially those containing metals like iron, can themselves be magnetic. As these grains form in the cool outer layers of the dying star, they can become aligned by the local magnetic fields. Once aligned, these dust grains then contribute to and can even strengthen the ambient magnetic field, creating a self-reinforcing cycle. This magneto-dusty interplay could be crucial for explaining the exceptional durability of the cometary knots. The magnetic fields, reinforced by dust, provide a skeletal structure that helps the knots maintain their integrity far longer than they otherwise could against the relentless pressure of radiation from the central star. This intricate dance between invisible forces and solid matter is a perfect example of how the Helix Nebula's beauty arises from the subtle interplay of multiple physical phenomena, each enhancing and shaping the other. Of all the puzzles the Helix Nebula presents, one of the most fundamental is a simple matter of accounting. When we add up all the mass we can see, the glowing ionized gas of the main ring, the dark dust, the molecular hydrogen in the knots, we arrive at a figure that is surprisingly low. The total comes to only about a third of the mass our Sun currently contains. This creates our 15th profound oddity, the case of the missing mass. It presents a serious cosmological puzzle because a star destined to become a white dwarf like the one at the helix's center must have started its life significantly heavier than our Sun, likely around twice its mass. Over its lifetime, it should have ejected the vast majority of that bulk into space. So, where did the rest of it go? The visible nebula we admire so much seems to be just the tip of a much larger and mostly invisible cosmic iceberg. The most promising solution to this mystery lies in the idea of a vast, faint halo surrounding the brilliant inner structure. The intense ultraviolet radiation from the central white dwarf is powerful, but its reach is finite. It can only ionize gas out to a certain distance, a boundary known as the ionization front, which defines the edge of the bright nebula we see. Beyond this front, the gas remains neutral, cold, and incredibly difficult to detect. It doesn't glow with the same vibrant energy. It's essentially dark matter, but in the literal sense of being unlit rather than the exotic, invisible kind that pervades the universe. This extended halo could contain the majority of the mass ejected by the star, material that was blown off in a slow, steady wind during the early red giant phase, long before the final, dramatic outburst that created the iconic glowing ring. This earlier ejector would have had more time to expand, becoming incredibly diffuse and faint, making it a tremendous challenge for our telescopes to spot. Evidence for this enormous halo is not just theoretical. Extremely long exposure photographs and observations with sensitive equipment have indeed revealed a faint, gargantuan glow extending far beyond the famous eye. This halo is not perfectly spherical. It shows subtle arcs and faint shells like ripples on a pond, each one marking a distinct episode of mass lost from the star in its final 100,000 years. Finding this missing mass in such a tenuous halo would solve the accounting problem, but it also rewrites the story of the star's death. It tells us that the beautiful planetary nebula phase is just the final, brightly lit act of a much longer and more gradual farewell. The main event we focus on is merely the last chapter, a brilliant flash that illuminates only the most recent ejector, while the bulk of the star's spent fuel has already drifted away into the darkness, forming a cosmic structure of immense scale that we are only beginning to map. Another compelling theory suggests that a significant portion of the mass might not be in a gaseous halo at all, but locked away in a different, even harder to detect form. A swarm of cold, Jupiter-sized planets or even smaller, failed stars known as brown dwarfs. During the star's red giant phase, its immense gravitational pull would have been weakened as it expanded. This could have destabilized the orbits of any outer planets in the system, flinging them out into the icy darkness of interstellar space. These orphaned worlds with no star to light them would be virtually invisible to our current telescopes. Alternatively, if the star had a low-mass binary companion, that star would still be there, hiding in the glare of the white dwarf. While we have not yet confirmed such a companion, its presence would immediately account for a sizable chunk of the missing mass. The hunt for this hidden partner, or for the infrared glow of cold, distant planets, is an active area of research, turning the Helix Nebula into a cosmic crime scene where astronomers are searching for hidden suspects that have yet to be revealed. This brings us to a phenomenon that is as ghostly as it is illuminating, a cosmic replay of the star's final moments that we are only just learning to see. Scattered throughout the vast volume of the Helix Nebula are shells of dust ejected by the star thousands of years before its final demise. When the star's core finally collapsed and the white dwarf ignited with its searing ultraviolet flash, that initial pulse of light raced outwards in all directions. The light that came directly toward us arrived centuries ago, announcing the star's death to the universe, but some of that light did not travel a straight path to Earth. Instead, it shot off in other directions, striking those ancient, distant dust shells. The light that hit these shells was then reflected, bouncing off at an angle and only now, thousands of years later, finally arriving at our telescopes. We call this a light echo, and it is essentially a delayed broadcast of the star's death scream, a signal that has taken a scenic route across the nebula to reach us. This creates a remarkable opportunity, turning the nebula itself into a time machine. By carefully analyzing this faint, echoed light, astronomers can dissect the properties of that initial flash with modern instruments that didn't exist when the light first reached Earth. They can measure its intensity, its spectrum, and its duration with a precision that would have been impossible in the past. This data acts as a forensic timestamp. Because we know the speed of light is constant, and we can measure the physical distance the echoed light has traveled compared to the direct light, we can calculate exactly how long ago the echo was created. This provides an incredibly accurate clock for pinning down the precise moment of the star's final transformation, allowing us to create a detailed timeline of the nebula's birth. But the echoes offer more than just a single timestamp. They provide a moving picture. Different dust shells are located at different distances from the central star. The light echoing from a shell that is 1 light-year away will arrive a year later than the light echoing from a shell half a light-year away. By observing how the echo propagates through the nebula over several years, astronomers can watch a wave of illumination sweep across these distant structures. This is like watching lightning illuminate different parts of a thunderhead in successive flashes, revealing the complex, three-dimensional architecture of the nebula's faintest, outermost regions. Each illuminated shell corresponds to a specific episode of mass loss from the star's past, allowing us to literally see its pre-death history being lit up layer by layer in a breathtaking delayed display. This phenomenon transforms the helix from a static portrait into a dynamic movie, with new scenes from its violent origin story still appearing on the sky. But the story of the Cometary knots becomes even more intriguing when we shift our perspective from a single snapshot to a multi-year time-lapse. While the entire nebula is expanding outward as a unified structure, meticulous observations have revealed that the knots themselves are not simply passive passengers on this cosmic journey. They exhibit their own individual, distinct movements, a phenomenon known as proper motion. This discovery uncovers our 17th oddity, transforming our view of these structures from static sculptures into dynamically evolving entities, each with its own unique trajectory and destiny. For decades, the prevailing assumption was that these knots were all moving in perfect lockstep, carried along by the general expansion of the nebula like leaves on a flowing river. However, when astronomers compared high-resolution images taken years or even decades apart, they noticed subtle but significant deviations. While most knots do follow the overall outward flow, a significant number are moving on slightly different paths. Some are accelerating faster than their neighbors, while others are drifting at a slight angle to the main current. A few even appear to be moving in ways that suggest they are interacting with one another, their trajectories subtly altered by their own local gravitational influences or by the pressure of the stellar wind acting on their irregular shapes. This proper motion is a powerful clue, revealing that the knots possess a degree of autonomy. They are not just frozen fossils, they are active participants in the nebula's evolution. Their individual movements are dictated by a complex combination of forces. The primary driver is still the immense pressure of the radiation and stellar wind from the central white dwarf, which acts like a constant breeze pushing against their surfaces. But the knots are not perfect, symmetrical spheres. Their shapes are irregular, with lumpy heads and wispy tails. This asymmetry means that the radiation pressure does not push on them evenly, creating a slight torque or a difference in force across their surface. Think of it like an oddly shaped sailboat. The wind will push it forward, but it might also cause it to drift slightly to one side. This effect, known as the rocket effect, can cause a knot to develop its own unique velocity vector over time. Furthermore, the knots are not all identical in mass and density. Some are more massive and compact, making them more resistant to being pushed around by the stellar wind. Others are lighter and more diffuse and are therefore accelerated more easily. This range of masses leads to a natural sorting process within the nebula. Over thousands of years, the lighter knots will be accelerated to higher speeds and may eventually overtake their heavier, slower-moving counterparts. This dynamic evolution means the population of knots we see today is just a single frame in a long movie. Their relative positions are constantly shifting, and some may even collide or merge, creating new, larger structures or fragmenting into smaller pieces. Witnessing this proper motion gives astronomers a rare opportunity to measure the nebula's dynamics in 3 dimensions. By tracking the movement of knots across the sky and combining that with spectroscopic measurements of their velocity toward or away from us, scientists can construct a full three-dimensional map of their trajectories. This data is invaluable for testing models of knot formation and survival. It allows researchers to input factors like radiation pressure, stellar wind strength, and knot density into simulations, and then check if the predicted motions match what we actually observe. The fact that the motions are complex and individualistic confirms that the environment within the nebula is far from a simple, uniform flow. It is a rich, dynamic ecosystem where local conditions dictate the fate of each structure. This oddity shows us that even in the aftermath of a star's death, the universe is teeming with intricate, small-scale motion, a constant and beautiful reminder that change is the only constant. Yet for all our detailed observations of the Helix Nebula's structure and motion, one of the most fundamental parameters has remained surprisingly elusive: its exact distance from Earth. This isn't just a matter of celestial cartography. It is a foundational puzzle that impacts our understanding of nearly every other aspect of this object. Traditionally, astronomers have cited a distance of about 700 light-years, a figure that makes the Helix one of the closest planetary nebulae to us. However, this number comes with a significant margin of error, and various measurement techniques have produced results that disagree, sometimes by as much as 200 light-years. This uncertainty creates our 18th oddity, a fundamental gap in our knowledge that ripples through every calculation we make about the nebula's true nature. The challenge of measuring cosmic distances is a classic problem in astronomy. For objects as relatively close as the Helix Nebula, one of the most reliable methods is trigonometric parallax. This technique works much like the way your eyes perceive depth. Imagine holding your finger in front of your face and closing one eye, then the other. Your finger appears to shift position against the background. Astronomers do the same thing on a galactic scale, observing the nebula from opposite sides of Earth's orbit around the Sun. They measure the tiny, apparent shift in the nebula's position against the backdrop of much more distant stars. The size of this shift, or parallax angle, allows for a direct geometric calculation of the distance. Space telescopes like Hipparcos and more recently Gaia have been dedicated to making these incredibly precise measurements. The data from Gaia, in particular, has suggested a distance that is slightly further than the traditional estimate, potentially placing the Helix closer to 750 light-years away. Why does a difference of 50 or 100 light-years matter so much? The answer lies in the chain of deductions that rely on this one number. The apparent size of the nebula in our sky is an angular measurement. It's how many arcseconds it spans. To convert that angular size into a true physical diameter, we absolutely need to know the distance. If the nebula is farther away than we thought, then its actual physical size is much larger than our previous estimates. A nebula that is 20% farther away must also be 20% wider to appear the same size in our telescopes. This immediately changes our perception of the scale of the event that created it. Furthermore, the brightness we measure from Earth is only the apparent brightness. To calculate the intrinsic luminosity, the true amount of light the nebula is producing, we must account for the dimming effect of distance. If the Helix is actually farther away, it must be intrinsically brighter and more energetic to appear as bright as it does to us. This, in turn, forces us to revise our models of the central star's power output and the physics of the ionization process. The problem is compounded by the fact that planetary nebulae are complex, evolving objects, not simple points of light. This complexity can confuse the very instruments designed to measure them. The Gaia spacecraft, for instance, excels at measuring the positions of single, point-like stars, but the Helix Nebula has a bright, extended structure with a central star that may be shrouded by dust or confused by nearby emission. These factors can introduce small but significant errors into the parallax measurement. As a result, some astronomers place more trust in alternative methods, such as using the expansion rate of the nebula itself. By measuring how fast the gas is moving away from the center using spectroscopy, and then carefully measuring how much the nebula has apparently grown in size over a period of many years, we can calculate a distance through a method called expansion parallax. This technique has sometimes yielded a shorter distance, adding to the ongoing debate and highlighting the difficulty of achieving a definitive answer. Resolving this discrepancy is not an academic exercise. It is essential for placing the Helix Nebula in its proper context within the family of planetary nebulae. Is it a typical example that just happens to be nearby, allowing us to see its details with exceptional clarity? Or is it an unusually large and luminous specimen, even for its class? Without a precise distance, we cannot accurately determine its mass, which is crucial for understanding the initial mass of the progenitor star and the efficiency of the mass loss process. This single number, the distance, is the master key that unlocks the true scale, energy, and evolutionary state of the entire system. The ongoing effort to pin it down exemplifies the meticulous, often frustrating, work that underpins our grandest cosmic discoveries, reminding us that even the most beautiful objects in the sky hold their deepest secrets closely. The presence of complex organic chemistry within the harsh environment of the Helix Nebula presents a startling contradiction. We have already seen how delicate molecular hydrogen can survive within the shielded hearts of the Cometary knots, but the story of cosmic chemistry goes much further. Scattered throughout the nebula, astronomers have detected the unmistakable infrared fingerprints of polycyclic aromatic hydrocarbons, or PAH. These are not simple molecules. They are large, sooty, carbon-based structures consisting of multiple benzene rings fused together in intricate patterns. Finding such sophisticated organic molecules in a region flooded with destructive ultraviolet radiation is like discovering a library of ancient, fragile manuscripts miraculously preserved in the middle of an active volcano. Their existence here forces us to reconsider the resilience of life's fundamental building blocks and the unexpected places where the universe chooses to assemble them. The significance of PAHs extends far beyond this single nebula. They are considered one of the most widespread types of molecules in the universe, found in interstellar clouds around other stars and even within our own Milky Way galaxy. They are essentially the basic skeletons of more complex organic matter, the charcoal-like starting point from which even more elaborate molecules can form. Under the right conditions, PAHs can act as stepping stones toward the prebiotic chemistry that leads to amino acids and the other ingredients essential for life as we know it. Therefore, discovering them in the Helix Nebula is not just about cataloging its chemical inventory. It connects the death of this star directly to the potential for life elsewhere. The nebula becomes a factory, taking carbon atoms forged in stellar nuclear fires and assembling them into structured organic compounds before scattering them back into the galactic ecosystem. But how do these complex molecules possibly form and endure in such an unforgiving place? The central white dwarf is a merciless source of high-energy radiation that should tear these large molecules apart. The answer lies in the same remarkable shelters we discussed earlier, the Cometary knots. Within the deep, cold, and densely packed cores of these knots, the conditions are surprisingly hospitable. Here, carbon atoms and smaller molecules, also ejected by the dying star, can stick to the surfaces of microscopic dust grains. Shielded from the brunt of the ultraviolet assault, these atoms have the time and stability to link up, forming the ring-like structures that grow into PAHs. It's a cosmic assembly line operating in the shadows, where the very structures that are being slowly destroyed on the outside are simultaneously creating the conditions for complex chemistry on the inside. The detection of these molecules also serves as a crucial clue about the chemical history of the progenitor star itself. The ability to form carbon-rich compounds like pHs hinges on there being more carbon atoms than oxygen atoms in the surrounding gas. If oxygen were more abundant, it would preferentially bond with carbon to form carbon monoxide gas, locking up the carbon and leaving little available to build complex hydrocarbons. The fact that pHs exist in the Helix Nebula suggests that in its final stages, this star became what astronomers call a carbon star. This occurs when convection currents dredge up carbon synthesized in the star's core and mix it into the outer layers. When these carbon-enriched layers were then ejected into space, they provided the raw material for this fascinating chemistry. The PAHs are, in effect, a final chemical testament to the internal processes that churned within the star during its last days. While the steady ultraviolet glow from the central star provides the main illumination for the Helix Nebula, it is not the only source of energy at work. Scattered throughout the structure, particularly in the turbulent inner regions, astronomers have identified pockets of gas that are glowing for a radically different reason. These zones are not simply fluorescing under starlight, they are being superheated by immense supersonic shock waves. This phenomenon marks our 20th profound oddity, revealing a layer of violence that operates in parallel to the more gentle process of photoionization, and it provides a unique window into the nebula's most energetic and chaotic interactions. To understand a shock front, picture a sonic boom but on a truly cosmic scale. Within the nebula, you have material moving at vastly different speeds. The fast wind from the white dwarf, racing outward at thousands of kilometers per second, represents one current. Slower moving shells of gas ejected during earlier, more gentle phases of the star's death represent another. When this fast-moving wind slams into the slower, denser material, it doesn't just push it aside gently. The collision is so violent that it creates a discontinuous, sharp boundary, a shock front. As gas crosses this boundary, it is compressed almost instantaneously, and the energy of its motion is converted directly into heat, raising the temperature of the gas to well over 1,000,000 degrees Celsius. This is fundamentally different from the 100,000-degree gas heated by starlight. This is matter heated by pure, unadulterated collision. The emission signature from this shock-heated gas is a dead giveaway for astronomers. Gas heated by starlight through photoionization glows with a specific set of emission lines corresponding to elements like hydrogen, oxygen, and nitrogen. But shock-heated gas reveals its nature through the relative intensity of these lines. The extreme temperatures and pressures within a shock front can rip electrons from atoms with such force that it creates a unique fingerprint in the spectrum. Certain emission lines, particularly from ions like doubly ionized oxygen, become exceptionally strong compared to what is seen in photoionized regions. This distinctive spectral signature acts as a cosmic thermometer, allowing scientists to not only identify the presence of shocks, but also to measure their incredible strength and speed. The location of these shock fronts within the Helix Nebula tells a specific story about its recent history. They are not uniformly distributed. Instead, they are often found along the inner edges of the main ring and in complex filamentary structures that lace the inner cavity. This placement is a crucial clue. It suggests that the fast wind from the white dwarf did not begin immediately after the star's final explosion. There was likely a brief period after the main ejection of the nebular shell where the central star was relatively quiet. Then, when the white dwarf fully ignited and its fast wind kicked in, this new supersonic outflow began to overtake the slower moving shell from behind. The resulting collision zone, where the fast wind rams into the slower shell, is precisely where we see the evidence for these violent shocks today. Studying these regions is like listening to the echoes of a cosmic demolition derby. The structure of the shock fronts, whether they are smooth and continuous or ragged and fragmented, reveals the density and uniformity of the gas they are plowing into. A smooth shock suggests a relatively homogeneous shell of material, while a complex, frayed shock front indicates that the wind is encountering a clumpy and irregular medium, much like the Cometary knots. This information is invaluable for reconstructing the exact sequence of mass loss events that occurred during the star's death throes. The shocks are therefore not just a byproduct of the nebula's dynamics, they are active probes, illuminating the conditions of the gas they travel through and providing a real-time look at the ongoing rearrangement of this cosmic landscape. But the very engine at the heart of this cosmic display, the central white dwarf, may hold a secret of its own, one that challenges our assumption of its steady, unvarying nature. While it appears as a stable point of light in our telescopes, there is intriguing evidence that the brightness of this stellar ember might not be constant at all. It could be a variable star flickering subtly over time. This possibility opens up a fascinating new line of inquiry, because a variable central star would imply dynamic processes are still very much alive within this system. Processes that could range from the star's own internal vibrations to the literal fall of matter onto its surface from a hidden source. One of the most plausible explanations for such variability lies in the star's own structure. White dwarfs are known to exhibit a phenomenon called pulsations. These are not explosions, but rather rhythmic, gentle expansions and contractions of the entire star, almost like a cosmic heartbeat. As the star pulsates, its surface area and temperature change slightly, causing its overall brightness to wax and wane in a predictable pattern. For astronomers, such pulsations are a gift. By carefully measuring the timing and amplitude of these brightness changes, they can perform a technique called astroseismology, which is akin to listening to the star's natural vibrations to understand its interior. The specific pulsation patterns act as a direct probe into conditions we could never otherwise see, revealing precise details about the star's mass, the thickness of its outer layers, and even its internal composition. If the helix's central star is pulsating, it will be communicating its deepest secrets through a silent, luminous code. However, pulsations are an internal mechanism. A different and perhaps more dramatic cause of variability would point to an external influence, the accretion of material. Imagine a disk of debris, the remnants of shattered planets or asteroids that survived the star's red giant phase, slowly spiraling inward due to the white dwarf's immense gravity. As chunks of this material are pulled onto the star's surface at a tremendous velocity, the impact releases sudden, intense flashes of light. Alternatively, the source could be a binary companion star. If the white dwarf has a stellar partner, it could be steadily siphoning a stream of gas from it. This gas would form a hot, swirling accretion disk around the white dwarf, and instabilities within that disk could cause the brightness to flicker. In either scenario, the variability would not be a gentle pulse, but a more erratic flickering, a sign of ongoing cosmic consumption. Determining the true cause is a major focus of observational campaigns. Astronomers monitor the star's light with extreme precision, looking for telltale signs in the pattern of its changes. A regular, periodic variation strongly suggests stable pulsations. A more irregular, burst-like pattern would be the hallmark of accretion events. The implications of each are profound. A pulsating star tells us about the end state of stellar evolution in isolation. An accreting star, however, reveals an active, interacting system, one that could potentially accumulate enough mass to one day trigger a Type Ia supernova, a titanic explosion that would briefly outshine its entire host galaxy. The question of whether this central light is steady or variable is therefore not a minor detail. It is a crucial diagnostic that could reveal whether the Helix Nebula is a quiet graveyard or a system still poised on the brink of a second, even more spectacular catastrophe. To peer even deeper into the hidden skeleton of the Helix Nebula, we must venture beyond the familiar realms of visible and infrared light into a part of the spectrum that feels almost alien, the submillimeter wave. These waves are longer than infrared light but shorter than radio waves, and they are the special signature of the coldest objects in the universe. When we point powerful telescopes like the Atacama Large Millimeter Array or ALMA toward the Helix, the nebula undergoes another dramatic transformation. The brilliant eye vanishes, and in its place we see an intricate, ghostly lacework of filaments and dense clumps, a structure that is completely invisible to optical telescopes. This submillimeter skeleton is our 22nd profound oddity, revealing a cold, dark component of the nebula that contains a significant portion of its total mass and tells a story of its earliest formation. The key to this hidden structure lies in the physics of cold matter. The gas in these submillimeter bright regions is not hot enough to glow from ionization or even warm enough to radiate significant infrared heat. Instead, what we are detecting is the faint thermal emission from vast clouds of cold dust grains, along with the specific radio waves emitted by certain cold molecules, most notably carbon monoxide. Carbon monoxide molecules, even when huddled in clouds only a few tens of degrees above absolute zero, are constantly vibrating and rotating. Each time they shift from a higher energy state to a lower one, they release a photon of light with a very specific wavelength that falls squarely in the submillimeter part of the spectrum. This makes carbon monoxide an excellent tracer, a cosmic dye that illuminates the otherwise invisible distribution of cold molecular gas. The intricate map that emerges is not just a faint echo of the visible nebula, it is a distinct and critical layer of its architecture. What ALMA and other submillimeter telescopes unveil is a level of complexity that challenges our imagination. The famous ring structure, so clear in visible light, is revealed to be just the illuminated edge of a much thicker, more convoluted disk of cold material. Filaments of cold gas, like cosmic tendrils, extend far beyond the bright ring, connecting regions and suggesting a turbulent history of ejection. Perhaps most importantly, these observations provide the clearest view yet of the dense cores of the Cometary knots. We can now see that each knot possesses an incredibly dense, cold heart of molecular gas and dust, a heart that is actively forming new, complex molecules in its protected interior. This data allows astronomers to precisely weigh these knots, confirming that they are not just wispy clouds but substantial structures, each containing a mass comparable to that of our entire Earth. This submillimeter view acts as a perfect complement to the story told by other wavelengths. The optical light shows us the present-day violence, the hot surface of the gas being actively sculpted by the central star's radiation. The infrared light shows us the warm dust, the memory of the star's past mass loss. But the submillimeter wave structure shows us the raw material, the cold, dark matter that represents the future. This is the reservoir of gas and dust that has not yet been reached by the ionization front. It is the pristine fuel that will, over the next several thousand years, be slowly heated, ionized, and incorporated into the glowing nebula, or else evaporated entirely back into the interstellar medium. By studying this cold component, we are essentially seeing the nebula's potential energy, the mass that has yet to be unleashed by the central engine. It completes our three-dimensional understanding, proving that the helix is not a hollow shell but a dense, layered entity, with its beautiful visible form being merely the brilliant surface of a far larger and more complex cosmic object. Now we turn our attention to a pattern so subtle you might miss it at first glance, but once seen, it becomes impossible to ignore. Looking at the thousands of cometary knots swarming the inner nebula, it's tempting to see a chaotic swarm. But a closer inspection reveals a startling degree of order. These knots are not scattered randomly like pebbles tossed in the air. Instead, they appear to be arranged along faint, spoke-like lines, all pointing directly back to the central star like the petals of a cosmic daisy. This radial alignment is a profound clue, a fossilized imprint of the very forces that shaped the nebula in its earliest, most violent moments. and it suggests that the initial ejection of material was far more structured than a simple spherical explosion. To understand why this alignment is so telling, we need to reimagine the star's final cataclysm. A perfectly symmetric outward blast would have sent a smooth, uniform shell of gas racing into space. Any instabilities that formed within that shell would be expected to create knots that are roughly similar in size and shape, but their positions and orientations would be random with no preferred direction. The fact that we see a clear radial pattern, a series of linear chains of knots, strongly indicates that the ejection was not smooth at all. It was likely riddled with density variations from the very beginning. Imagine the star's outer layers in their final moments before being cast off. Vast convective currents, like boiling water in a pot, would have been churning through the star's atmosphere. These currents create natural variations in density, with columns of slightly denser, cooler gas rising to the surface. When the final expulsion occurred, these pre-existing columns would have been the natural seeds for fragmentation, ejected as coherent streams of material rather than a homogeneous fog. This scenario points toward a specific type of instability known as Rayleigh-Taylor instability, which occurs when a lighter fluid pushes against a heavier one. In the case of the helix, the lighter fluid is the fast wind from the newly formed white dwarf, and the heavier fluid is the slower, denser shell of gas ejected just beforehand. As the fast wind rams into the slow shell, it doesn't push evenly. Instead, it finds the weakest points, the regions of slightly lower density, and punches through them. Meanwhile, the fingers of denser gas from the slow shell resist the push longer, becoming the bases around which the cometary knots eventually form. The resulting structure is a series of dense knots forming along the lines where the two winds interact most turbulently, naturally aligned in the direction of the push radially outward from the central energy source. The alignment is therefore a direct consequence of a directional, focused force acting upon a medium that was already subtly structured. There is, however, another compelling explanation that involves a much more dramatic shaping force, powerful jets. Early in the nebula's formation, before the white dwarf's current steady wind began, the central system might have experienced a brief but incredibly energetic phase where it fired off narrow, focused jets of material from its poles. These jets, traveling at a significant fraction of the speed of light, would have plowed through the surrounding, more slowly ejected gas, carving out cavities and creating strong shock waves that compressed the gas along their path. As the jets subsided, the material along these carved-out channels would have been preconditioned to fragment into the radially aligned knots we see today. In this model, the knots are not just a product of a general wind. They are the shrapnel lying along the scar lines left by a previous, more violent eruption. The radial alignment then becomes a permanent record of these fleeting, high-energy events, a ghostly echo of the jets that once roared from the dying star. Yet another chemical puzzle emerges when we perform a detailed inventory of the elements glowing within the Helix Nebula's gas. While we see strong signatures of oxygen, nitrogen, and carbon, one crucial element appears to be conspicuously underrepresented: iron. In cosmic terms, iron is a fundamental building block, a heavy element that is forged in the hearts of the most massive stars and scattered throughout the galaxy by supernova explosions. Our own solar system contains a substantial amount of iron. It's a key component of planetary cores, including Earth's. So, when spectroscopic analysis reveals a surprisingly low abundance of iron in the ionized gas of the helix, it forces us to ask a critical question: where did all the iron go? This isn't just a missing ingredient, it's a clue that points to two very different and equally fascinating explanations for the history of this system. The first possibility is that the star that created the Helix Nebula was simply born iron poor. Stars form from the interstellar medium, a cloud of gas and dust that has been enriched by generations of previous stellar explosions. The chemical composition of a star at its birth is therefore a permanent record of the conditions in that particular region of the galaxy at that specific moment in cosmic history. If the primordial cloud that collapsed to form the Helix's progenitor star happened to be deficient in iron, perhaps because it formed in a part of the galaxy that had been less thoroughly seeded by recent supernova, then the star would have carried that iron-poor signature throughout its life. When it died, it would have ejected this inherently iron-deficient material, creating the low abundance we observe today. This would make the Helix Nebula a unique time capsule, preserving the chemistry of a local galactic environment that existed billions of years ago. However, many astronomers find a second explanation more compelling. The iron isn't missing at all. It's simply hiding in a form that is incredibly difficult for our telescopes to see. The environment within a planetary nebula is a perfect factory for dust grains. As the ejected gas expands and cools, atoms of refractory elements, those with high melting points like silicon, carbon, and especially iron, can condense out of the gaseous state and form microscopic solid particles. Imagine a cloud of vapor cooling until tiny droplets of liquid form. In the nebula, it's a gas cooling until tiny specks of solid dust precipitate out. Iron is a prime candidate for this process. If the majority of the iron has condensed into these tiny dust grains, it would effectively vanish from our view in the optical spectrum. The spectroscopic lines we use to detect iron rely on the element being in a gaseous, ionized state. If the iron is locked up in solid, opaque grains, it no longer absorbs or emits light in those specific wavelengths, creating the illusion of a scarcity. The challenge then becomes finding this hidden iron. The most promising method is to search for its signature in the infrared. Cold dust grains absorb starlight and re-radiate the energy as heat in the infrared part of the spectrum. While it's difficult to distinguish iron dust from other types of dust like silicates or carbon compounds, sophisticated models can analyze the overall infrared emission to estimate the total mass of solid material. If that mass is significantly higher than what we can account for with other elements, it could point to a substantial reservoir of iron hiding in plain sight. Furthermore, if these iron-rich grains are large enough or coated with other materials, they might not even glow brightly in the infrared, instead remaining cold and dark, further complicating the search. This possibility transforms the mystery from a question of chemistry to one of material science, challenging us to understand the precise conditions under which different types of cosmic dust can form and survive. The implications of each scenario are profound. If the star was inherently iron-poor, it would suggest that the galactic neighborhood where our sun formed was unusually enriched with iron compared to other regions, perhaps due to a nearby supernova that injected heavy elements into our natal cloud just before the sun's birth. This would make our own solar system somewhat special. On the other hand, if the iron has simply condensed into dust, it reveals a critical and often overlooked phase of planetary nebula evolution, the rapid sequestration of heavy elements into solid form. This process is a key step in the galactic recycling of materials. The iron dust created in the Helix Nebula will eventually be blown out into the interstellar medium, where it may one day become part of new star systems. These tiny grains could serve as the building blocks for rocky planets around future stars, or even as catalysts for complex chemical reactions on their surfaces. The mystery of the missing iron, therefore, connects the death of one star directly to the potential birth of future worlds, highlighting the invisible threads that weave the cycle of cosmic creation and destruction. As we continue our descent into the Helix Nebula's deepest secrets, we must shift our gaze to a part of the light spectrum that is completely invisible to our eyes but is absolutely critical for understanding the violence at play. The ultraviolet light pouring from the central white dwarf is the primary engine that makes the entire nebula glow. But when we take this brilliant UV light and pass it through the most sophisticated cosmic prisms, breaking it down into its individual wavelengths, we encounter a series of baffling anomalies. The resulting ultraviolet spectrum is not a smooth, predictable curve. It is a jagged landscape of intense peaks and deep, unexplained valleys. These peculiar features are the spectral fingerprints of atoms and molecules being zapped by extreme energy, and some of these fingerprints simply don't match any known suspect in our cosmic database. The most significant of these anomalies are unexpected emission lines. An emission line is like a unique barcode for a specific element under specific conditions. It appears as a sharp spike in brightness at a very precise wavelength, indicating that a particular type of atom or ion has absorbed energy and then re-emitted it at that exact color. In the Helix's ultraviolet spectrum, astronomers have detected several prominent spikes that do not correspond to the usual suspects like hydrogen, helium, oxygen, or nitrogen. Instead, they point to the presence of much heavier and more complex ions, such as multiply ionized iron, silicon, and even carbon that has had 4 or 5 of its electrons stripped away. Creating these highly charged ions requires an environment of almost unimaginable ferocity, a place where the radiation field is so intense that it can blast apart atoms with ease, far exceeding what we would expect from the white dwarf's known surface temperature alone. This leads to a compelling puzzle. How can such highly ionized species exist so far from the central star? One leading theory suggests we are seeing the direct signature of a phenomenon called a shock ionization front. This isn't the relatively gentle heating from starlight. It's the brutal, sudden heating that occurs when a supersonic wind slams into a wall of slower-moving gas. At the boundary of this collision, the gas is compressed and heated to temperatures in the millions of degrees in an instant, creating a thin, incredibly hot layer where atoms are not just ionized, they are utterly shredded. The unexplained UV emission lines could be the dying scream of atoms caught in these localized zones of extreme violence, regions that are too small and transient to be seen directly, but whose powerful chemical signature is written across the ultraviolet sky. But the mysteries are not confined to bright emission lines. The spectrum also contains deep, dark absorption lines that are equally enigmatic. These are wavelengths where the light from the central star appears dimmer because specific elements in the space between the star and us have absorbed that particular light. Some of these absorption features are far too broad and deep to be explained by the diffuse gas of the nebula itself. They suggest the presence of dense, compact clouds of material located very close to the white dwarf, perhaps a swirling disk of debris or a persistent, high-density region in the stellar wind that acts like a natural filter, selectively blocking out certain colors of the star's intense ultraviolet glow. The precise pattern of these absorptions could be the key to mapping the invisible structure of this inner sanctum, revealing the geometry and composition of the material that is closest to the stellar corpse. Perhaps the most tantalizing possibility is that some of these spectral oddities are the signatures of molecular processes occurring in the most shielded environments. While it seems counterintuitive for delicate molecules to survive the UV onslaught, we know they can form in the deep shadows of the Cometary knots. Certain complex carbon-based molecules have absorption features that fall within the ultraviolet range. The detection of such features, even if faint, would be revolutionary. It would mean that the chemistry of life's building blocks is not only happening in the cold, dark cores of the knots, but is also leaving a faint, spectral imprint on the very light that is trying to destroy it. Each unexplained line in the ultraviolet spectrum is therefore a direct challenge to our models, a piece of a puzzle that points to a more dynamic, more violent, and perhaps more chemically rich environment than we have yet been able to imagine. If the Helix Nebula were an island, then the ocean it resides in is the interstellar medium, that incredibly thin soup of gas and dust that fills the vast spaces between the stars. For most of its visible existence, the nebula has been expanding into what is essentially a near-perfect vacuum, but nothing in space is truly empty. As the nebula's outermost halo continues its relentless outward march, it is beginning to encounter the genuine, albeit tenuous, material of the galactic environment. This interaction between the dying star's ejecta and the undisturbed interstellar medium is a slow-motion collision on an epic scale, and it represents a subtle but significant force that is starting to shape the nebula's final form. We can think of the expanding nebula as a powerful boat plowing through calm water. The boat creates a bow wave at its front and leaves a turbulent wake behind it. In an analogous cosmic process, the Helix Nebula might be generating its own version of these structures. As the leading edge of the nebula's faint outer halo pushes against the stationary interstellar medium, it could be compressing the interstellar gas, creating a dense, brightened shell known as a bow shock. This would appear as a faint, sharpened rim around the nebula's outermost boundary. Simultaneously, behind this leading edge, the motion of the nebula through the interstellar medium might be sweeping up material into a tail-like structure, similar to a comet's tail, stretching out behind it as it moves through the galaxy. Detecting these incredibly subtle features is at the very limit of our observational capabilities, but their potential existence would provide a direct map of the nebula's trajectory through space and the density of the galactic neighborhood it's passing through. This interaction is not merely a cosmetic effect, it has profound implications for the nebula's ultimate fate and expansion dynamics. The interstellar medium, however thin, exerts a gentle but persistent pressure like a constant, faint headwind. This pressure acts as a braking force on the nebula's expansion. The outermost material, which is the oldest and most diffuse, feels this drag effect most strongly. Over thousands of years, this will gradually slow the expansion of the nebula's halo, causing it to decelerate compared to the faster-moving inner regions. The nebula will not maintain its crisp, spherical shape indefinitely. Instead, the interaction is likely to cause it to become asymmetrical, with the side moving into the interstellar medium becoming compressed and flattened, while the opposite side may expand more freely. We are witnessing the very beginning of a process where the nebula ceases to be a distinct object and starts to blend back into the interstellar medium from which its progenitor star was born millions of years ago. The composition of the interstellar medium itself adds another layer of intrigue to this interaction. The material ejected from the Helix Nebula is chemically enriched. It's laden with heavy elements like carbon, oxygen, and nitrogen that were forged in the star's core. The surrounding interstellar medium, by comparison, is often more pristine, consisting primarily of hydrogen and helium. When these two different chemical soups mix at the boundary, it creates a unique environment for chemistry to occur. The shock fronts generated by the collision can provide the energy needed to trigger reactions between the nebula's complex molecules and the simple atoms of the interstellar medium. This region of interaction becomes a cauldron for new molecular formation, effectively seeding the local galactic environment with the enriched ashes of the dead star and contributing to the chemical evolution of the galaxy over billions of years. The Helix Nebula, in its final act, is not just fading away, it is actively fertilizing the space around it, ensuring that its elemental legacy will be incorporated into the next generation of stars and planets. Determining the precise age of the Helix Nebula, a task that seems straightforward, turns out to be one of its most persistent puzzles. We have two primary, independent cosmic clocks we can use to calculate when the central star met its dramatic end, but frustratingly, they don't always tick in perfect unison. This discrepancy forces us to question not just a number, but the very methods we use to measure cosmic time. The first and most intuitive method relies on the nebula's own expansion. We can measure the speed of the gas quite accurately using spectroscopy. We know it's rushing outward at about 30 kilometers per second. We can also measure the nebula's current angular size in our sky. By combining this apparent size with the nebula's distance from Earth, a number that itself is a subject of debate, we can calculate its true physical radius. The calculation is simple. If we know how big something is and how fast it's growing, we can rewind the clock to when it was just a point. This expansion age method typically gives us an estimate of around 10,000 years. Imagine then that the light we see today began its journey toward us around the time human civilizations were first establishing their earliest cities, a poignant connection between our history and a stellar death hundreds of light years away. The second method turns its attention to the central white dwarf itself. This stellar ember is not a static object. It is undergoing a slow and predictable process of cooling. When the white dwarf first formed, its surface was unbelievably hot, perhaps over 150,000 degrees Celsius. Since then, it has been steadily radiating its residual heat into space, with no internal nuclear fusion to replenish the loss. The rate at which it cools is governed by well-understood principles of physics relating to degenerate matter. By measuring the white dwarf's current temperature and modeling its cooling curve, we can estimate how long it has been since it was born from the star's collapsed core. This cooling age method, however, often suggests a slightly older age for the system, potentially pushing the event back to 12 or even 15,000 years ago. So why would these two clocks disagree? The answer likely lies in the fact that they are measuring two different events in a sequence, not a single instantaneous moment. The star's death was not a simple, instantaneous explosion. It was a prolonged process that could have stretched over thousands of years. The initial, slow shedding of the outer envelope during the red giant phase might mark the beginning of the cooling clock for the white dwarf as the hot core became exposed. The final, violent ejection that created the bright nebula we see, however, could have occurred significantly later. The expansion age measures the moment of this final, dramatic pulse. Therefore, the discrepancy isn't necessarily an error. It could be a valuable clue telling us that the star's death was a drawn-out affair with a long, slow sigh preceding its final shout. Resolving this age puzzle is crucial because it directly impacts our understanding of the speed and nature of the final stages of stellar evolution for Sun-like stars, providing a vital benchmark for testing our most sophisticated astrophysical models. To uncover the invisible architecture that guides the very dust and gas we see, we must learn to read a different kind of light. Ordinary light from the Helix Nebula vibrates in all directions, a chaotic jumble of waves. But some of that light arrives at our telescopes with a distinct, refined quality. Its waves are aligned, vibrating predominantly in a single plane. This is polarized light, and its subtle patterns across the nebula form our 28th profound oddity, acting as a natural compass that points directly to the hidden magnetic fields weaving through this cosmic expanse. The story these patterns tell is one of immense, organized force, a ghostly scaffold that has likely played a crucial role in sculpting the nebula from its very birth. The process that creates this polarized light is both elegant and precise. It involves the trillions of microscopic dust grains that float within the nebula. Many of these grains are not perfect spheres. They are elongated, almost needle-like in shape. In the presence of a magnetic field, these tiny grains experience a torque, a gentle but persistent twisting force that causes them to align themselves with their long axes perpendicular to the magnetic field lines. It's akin to how iron filings arrange themselves around a bar magnet, but on a truly cosmic scale. Once aligned, these dust grains act like a vast array of microscopic Venetian blinds. When the intense light from the central star strikes them, they preferentially scatter and reflect the light that vibrates in a specific direction related to their orientation. The light that makes its way to us from these regions is therefore polarized, its vibrational plane betraying the hidden alignment of the dust grains, which in turn maps the direction of the magnetic field itself. When astronomers meticulously chart the polarization patterns across the helix, they find a picture that is far from simple. A uniform dipole magnetic field emanating from the central star would create a neat, symmetrical pattern of polarization vectors like spokes on a wheel. Instead, the observed patterns are complex and often chaotic. In some regions, particularly within the inner lobes, the polarization vectors show a degree of order, suggesting magnetic field lines that are stretched and aligned by the general bipolar outflow. But in other areas, especially around the cometary knots and the faint outer filaments, the patterns become twisted and disorganized. This magnetic turbulence is a powerful clue. It suggests that the nebula's magnetic field is not a pristine, new structure generated by the white dwarf, but rather a fossil field, the amplified and tangled remnant of the magnetic field that was frozen into the star's outer layers when they were ejected thousands of years ago. This chaotic magnetic history helps explain several of the helix's other mysteries. The remarkable stability of the cometary knots, which should be evaporated by stellar radiation much faster than they are, can be attributed to the supportive framework of these magnetic fields. The fields provide a skeletal structure, a form of cosmic reinforcement that helps the knots maintain their integrity against the relentless external pressure. Furthermore, the very process of fragmentation that created the knots in the first place could have been guided by magnetic forces. As the slow, dense shell of gas was impacted by the fast wind from the white dwarf, pre-existing magnetic fields within the shell would have influenced where and how the instabilities developed, enhancing the formation of structures along specific directions and contributing to the radial alignment we observe. The polarization patterns are therefore not a secondary feature. They are the visible signature of an invisible hand that has been actively shaping the nebula's destiny at every stage of its evolution. Now, as we turn our attention from the grand geometry of the nebula to its most fundamental building blocks, we encounter a clue locked within the dust itself. The microscopic grains floating within the helix are more than just cosmic soot. They are time capsules, each one bearing the chemical signature of the environment in which it formed. When astronomers analyze the nebula's infrared glow, they detect a distinct and powerful signature of silicate dust. This finding is far from mundane. It is a direct message from the star's past, revealing a specific and critical chapter in its multi-stage life story. Silicates are essentially grains of rock, compounds of silicon and oxygen, similar to sand or quartz. Their presence in abundance tells us that the star which created the helix was, for most of its life, what astronomers call an oxygen-rich star. This classification hinges on a delicate cosmic balance. Inside a star, oxygen and carbon atoms are constantly competing to form molecules. If there are more oxygen atoms than carbon atoms, the oxygen will win, bonding with silicon to form silicate dust and with other elements, leaving little free carbon available. The clear detection of silicates is therefore a strong indicator that during its long red giant phase, the star's atmosphere contained more oxygen than carbon. This might seem like a minor chemical detail, but it has profound implications. It tells us that the nuclear fusion processes happening deep in the star's core did not, at that time, produce and dredge up enough carbon to overwhelm the available oxygen. The star's chemistry was in one state, and the dust it produced, the silicate dust we see today, is the frozen record of that state. However, the story does not end there. As we've seen, the nebula also contains evidence of complex carbon-based molecules, like polycyclic aromatic hydrocarbons. This presents a fascinating chemical puzzle. How can a single star produce both oxygen-rich silicate dust and carbon-rich organic molecules? The answer lies in the dynamic nature of stellar evolution. A star like the helix's progenitor is not a static chemical factory. As it ages and enters the final stages of its life, profound changes occur in its interior. The fusion of helium in the core creates new carbon atoms. In the star's final 1,000 years, powerful convective currents like gigantic cosmic elevators can carry this freshly synthesized carbon from the deep core up to the surface, enriching the star's outer layers. This process, known as the third dredge-up, can fundamentally alter the star's surface chemistry. If enough carbon is brought up, it can eventually tip the scales, making the carbon abundance greater than the oxygen abundance. When this happens, the star undergoes a dramatic transformation, crossing a threshold to become a carbon star. In this new chemical regime, carbon atoms readily link together, forming sooty compounds and graphite dust, while the available oxygen is quickly locked up in carbon monoxide gas. The presence of both silicate and carbon-based dust in the Helix Nebula suggests a remarkable history. The star lived most of its life as an oxygen-rich giant, producing the silicate grains during a long, steady mass loss phase. Then, near the very end of its life, it experienced a final dredge-up of carbon, briefly transforming into a carbon star and ejecting a shell of carbon-rich material. We are therefore seeing the layered results of this chemical evolution. The older, silicate dust represents the star's extended middle age, while the more recently formed carbon compounds are the signature of its final dramatic act. The nebula preserves both identities, a testament to a star that changed its essential nature right before its death. But the brilliant ring that defines the Helix Nebula's iconic appearance is merely the brightest chapter in a much longer story. If we dramatically lower the exposure on our telescopes, pulling back from the intense glow of the central region, an even grander structure emerges from the darkness. Encircling the entire nebula are multiple, incredibly faint concentric halos, like ghostly ripples expanding from a stone dropped into a galactic pond. These vast, ancient shells form our 30th profound oddity, and they represent a fossil record of the star's death throes, a series of separate mass loss events that occurred tens of thousands of years before the final, dramatic explosion that created the main nebula. To understand what we are seeing, we need to rewind the clock far back before the star's core collapsed. In the final million years of its life, a sun-like star does not die quietly. It enters a period of immense instability known as the asymptotic giant branch, or a GB phase. During this time, the star swells into a colossal red giant, so large that its outer layers are only weakly bound by gravity. Here, the star experiences a series of violent thermal pulses. These are not explosions in the traditional sense, but immense convulsions within the star's core where helium fusion ignites in sudden, runaway bursts. Each pulse sends a powerful shock wave through the star's interior, causing it to expand and contract violently. The consequence of each thermal pulse is a massive ejection of material. Imagine the star during a pulse, shuddering so violently that it blows off a significant portion of its outer atmosphere into space. This ejected material forms a spherical shell that expands outward. Then the star enters a quieter period, perhaps lasting 10,000 years, where a slower, steadier stellar wind continues to drift away. Just as this wind begins to wane, another thermal pulse rocks the star, ejecting another shell. Each of these shells expands into the void, with the newer shell eventually catching up to and plowing into the older, slower-moving one. The faint halos we see around the Helix Nebula are the preserved remnants of these separate ejection events. They are not being illuminated by the fierce ultraviolet light of the white dwarf. That light cannot reach them. Instead, they are visible due to the faint scattering of starlight off the immense quantities of dust within them, or through the subtle glow of molecular hydrogen that was formed in their cool, dense interiors long ago. The spacing and thickness of these halos provide a direct timeline of the star's final millennia. A series of thin, closely spaced shells suggests frequent, relatively gentle pulses. Thicker, more widely separated halos point to more violent but less frequent eruptions. By carefully mapping the geometry of these structures, astronomers can essentially read the star's medical chart, diagnosing the intensity and rhythm of its final, unstable heartbeats. This reveals that the beautiful planetary nebula phase we so admire is just the last page of a long and tumultuous autobiography. The main nebula is the final, brilliant shell ejected when the last thermal pulse stripped the star down to its bare core. The faint halos are the chapters that came before, the prolonged and dramatic prelude to the grand finale, now frozen in space as a permanent monument to the star's protracted and turbulent farewell. Yet to truly grasp the dynamic nature of the Helix Nebula, we must learn to see it not just as a static image, but as a three-dimensional movie. This is where the power of spectroscopy becomes our ultimate tool, allowing us to measure the motion of the gas itself. When we pass the nebula's light through a spectrograph, we don't just see its chemical composition. We see a series of spectral lines that act as precise speedometers. The physical principle at work is the Doppler shift, the same effect that causes a siren's pitch to drop as an ambulance races past you. Gas moving toward us shifts its light to shorter, bluer wavelengths, while gas moving away shifts it to longer, redder wavelengths. By meticulously mapping these subtle shifts across every point of the nebula, astronomers can construct a stunningly detailed velocity map, a dynamic portrait that reveals the helix is anything but a simple inflating bubble. What this kinematic map reveals is a scene of breathtaking complexity. The overall expansion is certainly there, with vast sections of the main ring redshifted, showing they are receding from us. But superimposed on this broad outward flow are intricate patterns that tell a far richer story. In certain regions, particularly along the inner edges of the ring and within the central cavity, we find gas that is dramatically blue-shifted, indicating it is rushing toward us at high velocity. This isn't a contradiction, it's a direct visualization of the nebula's double-lobed structure. We are looking almost directly down the barrel of one of the polar lobes. The gas in that lobe is expanding primarily in a direction across our line of sight, but the material at the very front and back of the lobe, where it curves toward and away from us, creates these blue and red shifts. This confirms that the iconic ring is indeed a thick equatorial torus, and the high-velocity gas we detect is the material that has been funneled out through the poles, creating a vast hourglass shape in motion. The surprises continue when we zoom in on specific structures like the Cometary knots. One might assume each knot is simply being carried along with the general expansion, a passive iceberg on a cosmic ocean current. But the velocity data shows something more fascinating. While the knots share the overall outward motion, many exhibit their own distinct internal velocity gradients. The dense head of a knot might be moving slightly slower than its own tail, or the entire knot might be drifting at a slight angle to the nebula's main flow. This indicates that these are not static fossils, they are dynamic entities experiencing their own unique forces. The pressure of the stellar wind is not uniform across their irregular surfaces, creating tiny torques that can alter their trajectories over time. Some knots even show signs of rotation, spinning slowly as they travel, a motion that could be a remnant of the angular momentum from the star system from which they formed. Perhaps the most profound kinematic mystery involves the central region itself. Detailed analysis sometimes reveals velocity components that are difficult to explain with a simple radial wind. There are hints of gas moving in ways that suggest not just outflow, but also inflow or even orbital motion around the central star. This is where the ghost of a binary companion becomes almost tangible. If the white dwarf has a partner, the gravitational dance between them would create a complex environment where streams of gas could be pulled from one star to the other, forming a swirling accretion disk. The spectral lines from such a disk would show a mix of redshifts and blue shifts, as one side of the disk spins toward us while the other spins away. While the signal is faint and challenging to disentangle from the broader nebula motions, its potential presence would be a smoking gun, revealing that the heart of the helix is not a solitary corpse but an active, interacting binary system, continuing to shape its surroundings long after the main eruption. This kinematic structure transforms the nebula from a beautiful fossil into a living, breathing entity, its every motion a silent testament to the powerful forces that gave it birth. Beneath the broad brushstrokes of the Helix Nebula's expansion and the violent shock fronts lies a more subtle, almost stealthy, light-producing mechanism that is crucial for understanding its true spectrum. This process is known as charge exchange, and it represents a unique form of atomic interaction that becomes exceptionally important in the complex, mixed environment of a planetary nebula. At its heart, charge exchange is a straightforward, if dramatic, transaction. Imagine a fast-moving, highly charged ion, an atom that has been stripped of one or more of its electrons racing through space. This ion is desperate to regain a state of electrical balance. When it crosses paths with a neutral, slow-moving atom or molecule that still has all its electrons, the ion can essentially mug the neutral particle, stealing an electron right from it. This act of atomic theft is the charge exchange. The consequence of this exchange is profound for the particles involved and for the light we detect. The formerly charged ion, now neutralized, often ends up in a highly excited state because of the energy involved in the transfer. A fraction of a second later, it relaxes back to a calm state, releasing that excess energy by emitting a photon of light at a very specific wavelength. Meanwhile, the victim of the theft, the atom that just lost an electron, is now itself a charged ion, but it may be left in a different energetic state than if it had been ionized by a UV photon. This entire sequence produces a very distinct pattern of emission lines in the nebula's spectrum, a pattern that is the unique fingerprint of the charge exchange process. It's a light signature that astronomers can hunt for, and in the Helix Nebula they have found it to be remarkably strong. What makes charge exchange so significant in the helix is the specific environment it reveals. For this process to be efficient, you need a region where hot, highly ionized plasma and cold, neutral gas are in intimate contact. This is not a common situation in most of space. Typically, these two phases of matter are separated. But the Helix Nebula is a masterpiece of mixed conditions. The fierce ultraviolet radiation from the central white dwarf has created a vast bubble of hot, ionized plasma, the bright glowing gas we see so clearly. However, peppered throughout this hot plasma are the thousands of Cometary knots, which act as dense, cool islands of neutral gas, shielding complex molecules in their cores. The boundaries where the scorching plasma washes up against the cold shores of these knots are the perfect breeding grounds for charge exchange. It's in these turbulent interfaces that ions from the hot wind can readily snatch electrons from the neutral atoms boiling off the knots. This process helps solve a particular spectroscopic puzzle. Astronomers had long observed certain emission lines in the helix, especially from ions like oxygen and nitrogen that were unusually bright. The standard model of photoionization, where UV light simply knocks electrons off atoms which then glow as they recapture them, could not fully account for the intensity of these lines. The energy just didn't add up. Charge exchange provided the missing piece, because the energy transfer in a charge exchange collision can be more efficient at populating the specific energy levels that lead to these bright lines. It acts as an amplification mechanism. It's as if the nebula has a second, more specialized power source for certain colors of light, one that operates only in the narrow zones where different states of matter violently meet. By factoring in charge exchange, models of the nebula's emission finally align with observations, providing a much more accurate picture of its physical and chemical conditions. The detection of strong charge exchange emission has implications that reach far beyond simply solving a spectral anomaly. It acts as a direct probe, allowing scientists to map the otherwise invisible interactions between the nebula's different components. The strength of the charge exchange signal tells them about the density and temperature of the plasma at the surfaces of the Cometary knots. It provides a way to measure the rate at which material is being eroded from the knots and mixed into the hot wind. This makes charge exchange not just an interesting curiosity, but a vital diagnostic tool for understanding the life cycle and stability of these iconic structures. It reveals a continuous, microscopic dance of energy and matter happening across the nebula, a fundamental process that contributes to the beautiful and complex light show we see from Earth. Now we come to a concept that connects the death of one star to the birth of another, a fascinating parallel that exists across the cosmos. When we observe the famous Cometary knots of the Helix Nebula, with their dense, glowing heads and long, streaming tails, they bear a striking and almost uncanny resemblance to objects in a very different cosmic nursery, the proplyds or protoplanetary disks found in the Orion Nebula. This visual similarity is more than just a coincidence. It points to a universal physical process, even though the environments and ultimate fates of these structures could not be more different. In the Orion Nebula, proplyds are cocoons of gas and dust surrounding young, newly formed stars within which planets are actively coalescing. They are sites of creation. The helix knots, by contrast, are the fragmented remnants of a star's death shroud, existing in a far more hostile and transient environment. Yet, the comparison is irresistible and scientifically fruitful, forcing us to consider the possibility that even in the aftermath of destruction, the seeds for new worlds might be sown. The physical mechanism that shapes both types of objects is fundamentally the same: the interaction between a strong source of radiation and a dense clump of gas and dust. In Orion, the proplyds are illuminated and sculpted by the intense ultraviolet light from a cluster of massive, hot young stars. The radiation erodes the outer layers of the gas disks, boiling off material and creating a bright ionization front at the head, while the pressure of the stellar wind pushes the evaporated gas into a long, comet-like tail. In the helix, the role of the sculpting star is played by the central white dwarf, and the dense clumps are the surviving fragments of the deceased star's atmosphere. The same interplay of radiation pressure and photoevaporation is at work, producing structures that are morphologically twins, despite being born from opposite ends of the stellar life cycle. This shows that the universe often reuses its most effective patterns, applying them to vastly different scenarios. This comparison leads to a truly tantalizing, albeit speculative, idea. Could some of the helix's cometary knots, in their incredibly dense and shielded cores, be hosting nascent planetary systems? We know that these knots contain the essential ingredients. They are rich in molecules, dust, and ices. Under the right conditions, the dust grains within a knot could begin to stick together, forming larger and larger bodies through a process known as accretion. The knot itself would act as a vast, if temporary, protoplanetary disk. However, the environment is exponentially harsher than that of a proplyd in Orion. The central white dwarf is a far more punishing source of high-energy radiation than a young O-type star, and the entire system is expanding outward, destined to dissipate within a few tens of thousands of years. This is a cruelly short time frame for the slow, gradual process of planet formation, which typically takes millions of years. Therefore, while the basic ingredients and physical conditions for planet formation might theoretically exist within a knot, the odds are overwhelmingly stacked against it. Any planetary embryos that did begin to form would likely be stripped of their gaseous envelopes and sterilized by the intense radiation long before they could grow into full-fledged planets. The most probable outcome is that the knots will simply evaporate, scattering their enriched contents back into space. Yet, the mere possibility invites us to imagine a profound cycle. The heavy elements and complex molecules within these knots, the very elements forged in the star's core, are the raw materials for future planets around other stars. So, while a knot may not successfully form its own planets, it is actively contributing its legacy to the galactic reservoir from which the next generation of planetary systems will draw. The helix's knots are not planet-forming factories themselves, but rather delivery vehicles, ensuring that the ashes of the dead star will one day be incorporated into new worlds, completing a grand cosmic cycle of death and rebirth. Within the chaotic and chemically rich environment of the Helix Nebula, astronomers have been hunting for a ghost, a molecule so fundamental to cosmic history that its detection here would forge a direct link between the death of a single star and the birth of the entire universe. This molecule is helium hydride ion, written as He+, and it holds the distinguished title of being the very first type of molecule to have formed after the Big Bang. The tentative detection of its spectral signature within the helix is not just another item on a list of chemical components. It is a profound connection to our cosmic origins, a whisper from the dawn of time echoing within a modern stellar graveyard. To understand why this molecule is so special, we need to travel back to a time when the universe was a mere infant, less than 100,000 years old. After the initial fireball of the Big Bang began to cool, the cosmos was a dark, opaque sea of primordial plasma, a soup of nuclei and electrons too energetic to combine. As expansion continued and temperatures dropped further, electrons were finally captured by nuclei to form the first atoms, primarily hydrogen and helium. But the universe was still far too hot and hostile for normal chemistry. Neutral hydrogen atoms, the most abundant substance, require a very specific and relatively low energy process to form a bond with another atom. For a brief window of time, the only chemical reaction that was possible involved a more aggressive partner. A helium atom, once ionized by the lingering background radiation, could snatch a lone electron from a passing hydrogen atom. This created the helium hydride ion, a fragile, positively charged molecule that marked the very beginning of chemistry itself. It was the first time two different atoms had linked together in the young cosmos, paving the way for all the complex molecules that would follow. For decades, He+ existed only in theory and computer models of the early universe. Detecting it in the modern cosmos proved incredibly difficult because it is so reactive and unstable. It gets destroyed almost instantly in most environments, especially where neutral hydrogen is plentiful, as it will readily transfer its proton to a hydrogen atom, forming a molecular hydrogen ion. The quest to find it was a major goal of astrophysics. The Helix Nebula, with its unique and extreme conditions, presented a perfect, if unexpected, hunting ground. The environment here is strangely analogous to the early universe. The central white dwarf bathes the nebula in intense ultraviolet radiation that keeps the surrounding gas highly ionized. In these hot, harsh zones, neutral hydrogen is scarce, and helium atoms are stripped of an electron, creating the exact conditions where He+ can form and, crucially, survive long enough to be detected. The search culminated with observations from powerful airborne and space-based observatories, which detected a specific spectral line in the far infrared that is the unique fingerprint of the helium hydride ion. While the detection is considered tentative and requires further confirmation, its potential presence is a monumental discovery. It demonstrates that the chemical pathways that operated in the primordial universe are not just a historical footnote, they are still active today in specialized environments. The Helix Nebula acts as a natural time machine, recreating the physical conditions of the cosmos's first chemical steps within its own expanding shell. This means we can study the properties and behavior of this ancient molecule, not just in theory, but in a real, observable laboratory. The significance of this find extends far beyond simply ticking a box on a cosmic checklist. It validates our fundamental understanding of the chemical evolution of the universe. The fact that we can observe He+ in a context that matches our theoretical predictions so well gives us tremendous confidence in our models of the early universe. Furthermore, it highlights the Helix Nebula's role as a crucible for exotic chemistry. The molecule's presence is a direct result of the immense power of the central star, which is effectively resurrecting a long-lost chapter of cosmic history. In this sense, the death of the star is not an end but a transformation that allows us to witness the beginnings of molecular life, connecting the final breath of a sun-like star directly to the first chemical bonds that ever formed billions of years ago. While the brilliant glow of the nebula captures our attention, a more subtle thermal story is unfolding across its vast expanse, one that is written in the heat of countless dust grains. This narrative of temperature reveals a dramatic gradient, a cosmic slide from inferno to deep freeze that provides a powerful, indirect map of the radiation field and the density structure that defines the helix. If we could feel the temperature of these microscopic particles, we would experience an astonishing range, from grains being superheated to over 100,000 degrees Celsius in the immediate vicinity of the white dwarf, to particles chilled to just a few tens of degrees above absolute zero within the shielded hearts of the distant Cometary knots. This incredible thermal range is not random. It is the direct and predictable consequence of a simple, universal principle. The intensity of starlight decreases with the square of the distance from its source. However, the actual temperatures we observe tell a much richer story about the environment each grain inhabits. The physics governing this thermal gradient is beautifully straightforward, yet its application paints a complex picture. A dust grain in space heats up by absorbing the energy from photons of light striking its surface. It cools down by re-radiating that energy away as infrared light. The grain will reach an equilibrium temperature when its rate of absorption exactly matches its rate of emission. Near the central star, the flood of ultraviolet and visible photons is so intense that the grains are bombarded relentlessly, forcing them to a scorching equilibrium. As we move outward, the number of photons per square inch drops dramatically, and the grains have more time to radiate their energy away into the void, leading to a steady cooling. This would create a smooth, predictable temperature gradient in a perfectly empty and uniform nebula. But the helix is anything but uniform, and the deviations from this smooth gradient are where the true secrets lie. The most significant factor disrupting this smooth gradient is the very structure of the nebula itself, its complex density variations. The Cometary knots are the prime example. A knot is not a solid object, it is a vast cloud with a steep density profile. The outer layers of the knot facing the star are indeed hot. They absorb the brunt of the radiation, reaching temperatures high enough to make them glow brightly in the infrared. But just a short distance into the knot, the density of gas and dust increases so dramatically that it becomes an effective radiation shield. Photons from the central star are progressively absorbed by the outer layers, their energy depleted before they can penetrate deeply. This creates an incredibly sharp temperature drop within the knot itself. The core of a large cometary knot can be over 1,000 times colder than its sun-facing surface. This thermal structure turns each knot into a natural thermostat with a hot shell and a frigid interior, demonstrating how local density can create microclimates that defy the simple distance-based rule. This detailed temperature map, constructed from infrared observations, is an invaluable tool for astronomers. By carefully measuring the color of the infrared emission, that is, which specific infrared wavelengths are brightest, scientists can accurately determine the temperature of the dust at every point in the nebula. A hotter grain emits more of its light at shorter infrared wavelengths, while a cooler grain peaks at longer wavelengths. This data allows researchers to perform a kind of cosmic audit of the radiation field. If the dust in a particular region is cooler than the simple distance law would predict, it indicates that something is blocking or attenuating the starlight. This could be a previously unseen filament of gas or a particularly dense concentration of dust casting a shadow. Conversely, dust that is hotter than expected might be located in a low-density cavity where it has an unobstructed view of the star, or it could be heated by an additional energy source, such as a shock wave from a fast-moving wind. The dust temperature gradient, therefore, acts as a precise diagnostic, revealing the intricate architecture of the nebula in a way that visible light images alone cannot. It shows us the hidden contours of density and the true reach of the central star's energetic influence, proving that even in death, a star's light meticulously sculpts its surroundings, writing its history in the heat of a trillion tiny worlds. Perhaps the most compelling explanation for the Helix Nebula's intricate shape and energetic behavior lies not with a single star, but with a pair locked in a gravitational dance. The binary star hypothesis proposes that the central white dwarf is not alone. It has a companion, and this hidden partnership is the primary architect behind nearly every oddity we have encountered. The perfectly bipolar structure, the high-velocity jets, the potential X-ray emission from an accretion disk, all of these point toward a dynamic interaction that a solitary star would struggle to produce. The gravitational influence of a second body provides the most elegant mechanism for breaking the spherical symmetry that a star's death would otherwise possess. Imagine the system in its final millennia. The primary star, having exhausted its core hydrogen, begins to swell into a red giant. If a companion star is orbiting relatively closely, it eventually finds itself engulfed within the giant's tenuous but immense outer atmosphere. This is not a peaceful merger. The companion star, dense and compact, begins to plow through this superheated fog, creating immense friction and drag. This interaction does two critical things. First, it siphons material from the giant onto the companion, often forming a temporary accretion disk. Second, and more importantly for the nebula's shape, the orbital motion of the companion acts like a cosmic egg beater, channeling the giant's expelled material outward along the star's rotational axis. The result is a powerful focusing of the outflow into two opposing jets or lobes, perfectly explaining the bipolar hourglass shape we observe today. The dense equatorial torus we inferred is then simply the debris that was not funneled by this process, the material left behind in the orbital plane. The evidence for this scenario is compelling, yet the companion itself remains frustratingly elusive. Directly spotting a faint star so close to the brilliant glare of the white dwarf is a monumental observational challenge. Astronomers have employed a variety of sophisticated techniques in the hunt. They look for subtle, periodic wobbles in the motion of the white dwarf that would betray the gravitational tug of an unseen partner. They analyze the star's light for tiny, regular dips in brightness that might occur if a companion transits or passes in front of it from our perspective. So far, these searches have yielded no definitive proof, which only deepens the mystery. The companion could be a small, dim main sequence star, a fellow white dwarf, or even a neutron star, each of which would be incredibly difficult to detect against the bright backdrop of the nebula. The absence of direct evidence has led to alternative, albeit less comprehensive, theories. Some models suggest that a very strong magnetic field, generated by the rapidly spinning core of the dying star, could have channeled the ejector into a bipolar shape without the need for a binary companion. However, while magnetism can certainly shape and sculpt, it is the binary interaction that most naturally provides the initial kick to break the symmetry so dramatically. The ongoing search for the companion is therefore one of the most active frontiers in the study of the Helix Nebula. Confirming its existence would not just solve a single puzzle, it would provide a unified explanation for the nebula's form, its high-energy phenomena, and its ongoing activity, turning a beautiful cosmic mystery into a textbook example of how binary stars govern the final acts of stellar evolution. But to fully appreciate the intricate chemistry of the Helix Nebula, we must zoom in on the very battlegrounds where light and matter are in constant conflict. These are the photodissociation regions, or PDRS for short, and they form our 37th profound oddity. A photodissociation region is not a specific location you can point to on a map. It is a dynamic interface, a razor-thin zone that exists wherever the harsh ultraviolet light from a hot star slams into a cloud of cold, neutral gas. Within this boundary layer, a relentless microscopic war is waged. The energetic UV photons act like tiny bullets, striking molecules and breaking the chemical bonds that hold them together, a process known as photodissociation. The Helix Nebula is an almost perfect natural laboratory for studying these regions because its structure presents them to us on a truly monumental scale with incredible clarity. The importance of PDRS extends far beyond this single nebula. They are fundamental to understanding the life cycle of galaxies. These regions are the factories where the interstellar medium is constantly being recycled and reformed. They dictate the balance between atomic and molecular gas, control the heating and cooling of vast clouds, and set the stage for the formation of new stars. In the grand spiral arms of galaxies like our Milky Way, PDRS are ubiquitous, but they are often complex, overlapping, and difficult to observe in isolation. The Helix Nebula, by contrast, offers a pristine, relatively simple, and beautifully illuminated example. Its geometry is well-defined. Its energy source is a single, brilliantly characterized white dwarf, and its distance is close enough for our telescopes to resolve the intricate structure of these dissociation fronts. It's as if the universe has provided us with a perfectly prepared slide under a cosmic microscope. Within the helix, the most spectacular PDRS are found on the surfaces of the Cometary knots. Picture one of these trillion-mile-wide structures. Its core is a dark, cold sanctuary where complex molecules can form and survive. But the side facing the central star is a completely different world. Here, the gas is exposed to the full, unfiltered fury of the ultraviolet radiation. This creates a sharp transition, a layer of hot, ionized gas on the very surface, where atoms are stripped of their electrons, followed immediately by the photodissociation region itself. In this thin shell, molecules like molecular hydrogen are being torn apart as fast as they can form. The energy from the dissociating molecules is then re-radiated, creating a faint but detectable glow in specific infrared wavelengths that serves as a beacon, marking the precise location and physical conditions of this violent interface. By studying the emission from these PDRS, astronomers can measure the intensity of the stellar radiation field with remarkable precision. They can determine the density of the gas at the knot's surface and calculate the rate at which material is being evaporated away into the surrounding nebula. The structure of the PDR also reveals the history of the knot. A sharp, well-defined dissociation front suggests a knot that has been exposed to the stellar wind for a consistent period. A more ragged or irregular front might indicate that the knot is rotating or that its surface is uneven, leading to variations in how quickly it is being eroded. In this way, the photodissociation regions act as real-time diagnostics, showing us not just the destructive power of the central star, but also the resilience and internal dynamics of the structures it is trying to destroy. But if you were to look at the Helix Nebula through a telescope that separates light into its constituent colors, you would witness a spectacle dominated by a single, brilliant hue. The most intense light pouring from this cosmic eye is not the classic red of hydrogen or the blue of oxygen, but a specific, vibrant shade of green. This is the signature of doubly ionized oxygen, an emission line that astronomers designate as O3. The sheer dominance of this green glow is not an aesthetic coincidence. It is a direct and powerful reading of the extreme physical conditions within the nebula, a precise measurement of the violence being wrought by the central star. To understand why this particular color shines so brightly is to understand the very engine of the nebula's luminescence. The key lies in the process of ionization and the specific energy required to achieve it. An oxygen atom normally has 8 electrons orbiting its nucleus. When we say it's doubly ionized, it means it has lost 2 of those electrons, leaving it with a strong positive charge. Stripping away not one, but two electrons from an atom requires a tremendous amount of energy. The ultraviolet photons from the central white dwarf must be extremely energetic, which directly relates to the star's scorching surface temperature of over 120,000 degrees Celsius. A cooler star simply could not produce photons powerful enough to create significant amounts of O3. Therefore, the intensity of this green light acts as a built-in thermometer, confirming the ferocious heat of the stellar corpse at the heart of the system. It is a direct consequence of the star's evolutionary state, a beacon signaling the presence of a newly formed, incredibly hot white dwarf. However, temperature alone is not the full story. The O3 line is also exquisitely sensitive to the density of the gas. In a very dense environment, an oxygen atom that has been doubly ionized doesn't have much time to relax and emit its characteristic green photon before it collides with another particle. These collisions can excite the atom without it emitting light, effectively robbing us of the glow. The fact that the O3 emission in the helix is so extraordinarily strong tells us that the gas in the main glowing regions is actually quite tenuous. It exists in a low-density state known to astronomers as the low-density limit, where atoms are spaced far enough apart that they can radiate their energy away freely through light emission rather than losing it through collisions. This combination of a high-energy radiation source and a low-density gas cloud creates the perfect breeding ground for the O3 line to flourish, making it the visual superstar of the nebula. This delicate balance has a fascinating consequence for how the nebula appears in different filters. If you were to photograph the helix using a filter that isolates the red light of hydrogen alpha, you would see a beautiful, extended structure. But if you then switch to a filter that only lets through the green O3 light, the nebula seems to transform. The O3 emission is often more confined to the inner, brighter edges of the rings and filaments. This is because the O3 producing process requires the most intense UV radiation, which diminishes rapidly as you move outward from the central star. The hydrogen emission, being easier to produce, can persist further out into the fainter regions. This variation in distribution creates a subtle but important layered effect, with the green O3 light tracing the zones of most intense illumination and the red hydrogen light outlining the nebula's full, extended body. It is a spectral map that reveals the gradient of stellar energy washing across the expanding shell of gas. The prominence of the O3 line also places the Helix Nebula in a broader astronomical context. It is a classic example of what is known as a high-excitation planetary nebula. This classification helps astronomers compare it to other nebulae and understand the properties of their central stars. A nebula with weak O3 emission likely harbors a cooler, older white dwarf. The helix, with its brilliant green glow, is clearly in a younger, more energetic phase of its post-stellar life. This single spectral feature, therefore, does more than just create a beautiful image. It serves as a critical diagnostic tool, allowing scientists to quickly gauge the age, temperature, and evolutionary state of the entire system, connecting this one celestial object to the vast family of stellar remnants scattered throughout our galaxy. The fate of these cometary knots is a question that pits the relentless power of starlight against the stubborn resilience of matter itself. Each knot is locked in a slow-motion battle for survival, and the ultimate outcome is not merely an academic curiosity. It is a demonstration of fundamental astrophysical processes that shape the life cycle of material throughout the galaxy. On one hand, the forces arrayed against them are immense and inescapable. The central white dwarf is a permanent and unyielding source of destructive energy, bathing the knots in an ultraviolet furnace that methodically strips atoms from their outer layers. This process, known as photoevaporation, is like a cosmic sandblaster steadily eroding the knots away. The long, glowing tails we see trailing behind them are not just for show. They are the visible evidence of this ongoing disintegration, a stream of material being boiled off and swept away by the stellar wind. Based on current erosion rates, astronomers estimate that most of these majestic structures have a lifespan measured only in tens of thousands of years, a mere heartbeat in cosmic time. They are temporary phenomena destined to dissipate and merge back into the hot, diffuse plasma of the expanding nebula, their unique structures lost forever. However, this grim forecast may not be the final word for every knot. The key to a different destiny lies in their remarkable density and the powerful force of self-gravity. While radiation pressure from the star is trying to tear them apart, the knot's own inward pull of gravity is trying to hold them together. For the largest and most massive knots, there exists a tantalizing possibility. If a knot is dense enough, its self-gravity could become strong enough to overcome both the radiation pressure trying to push it apart and the internal gas pressure that supports it against collapse. In this scenario, a knot would not simply evaporate, it would undergo a gravitational collapse. It would contract, becoming ever denser and darker, eventually cutting itself off from the surrounding nebula. What was once a brilliant, glowing finger of gas could transform into a compact, isolated globule of cold molecular gas and dust, a dark, free-floating cloud adrift in the interstellar void. These hypothetical survivors are known as Bok globules, named after the astronomer who first studied them. A Bok globule is a cold, dark cloud so dense that it blocks out the light from stars behind it. If the Helix's knots were to undergo this transformation, they would essentially be ejected from their dying stellar system, becoming nomadic orphans in the galaxy. They would no longer glow with the light of the central star. Instead, they would be visible only as black silhouettes against brighter backgrounds or by their faint emission in the radio and submillimeter wavelengths. This would be a profound metamorphosis, from a brilliant feature of a stellar death shroud to a dark, independent entity embarking on its own cosmic journey. The implications of this second path are staggering. Within the cold, dense, and shielded environment of such a globule, the conditions would be ideal for the formation of new stellar systems. The same complex organic molecules and ices we know exist within the knots today would be preserved and concentrated. Over millions of years, gravity could continue its work, causing the globule to fragment and collapse further, potentially giving birth to low-mass stars, brown dwarfs, or even planetary systems. This idea connects the death of one star directly to the birth of future suns. The heavy elements forged in the progenitor star's core, the carbon, oxygen, and nitrogen that are the building blocks of planets and life, would be safely packaged within these dark globules, carried across the galaxy to seed new worlds. The Helix Nebula, therefore, would not just be a tomb, it would also be a nursery, its most resilient structures becoming the cradles for the next generation. The ultimate fate of the knots is a question that remains open, a race between evaporation and gravitational collapse that will determine whether these beautiful structures are merely ephemeral wonders or the seeds of cosmic futures yet to come. And so we come to the final and perhaps most profound oddity of all, one that encompasses the entire purpose of this magnificent structure. The Helix Nebula is far more than a cosmic graveyard or a beautiful astronomical portrait. It is a grand, dynamic symbol of cosmic recycling on a galactic scale. Every strange feature we have explored, from the complex chemistry in the Cometary knots to the high-velocity jets and the unexplained X-ray glow, is part of a single, overarching story. This is the story of how a star, in its death, meticulously packages and disperses the very elements that are essential for the universe's future. The oddities within its core are not merely curiosities for our scientific inquiry. They are the dispersed seeds from which new stars, new planets, and perhaps even new life will one day grow. Consider the journey of a single atom of oxygen, forged under immense pressure and temperature deep within the star's core. For billions of years, it was trapped, playing its role in the nuclear fusion that kept the star shining. When the star could no longer support itself, this atom was blasted out into the void, a speck in the expanding shell of the nebula. It might have found itself in one of the Cometary knots, where it combined with other atoms to form a silicate dust grain. For thousands of years, it resided in the deep freeze of that knot's heart, sheltered from the radiation that filled the surrounding space. Eventually, as the knot evaporates, that dust grain will be released, joining the vast reservoir of the interstellar medium. There it will drift for millions of years until the gentle pull of gravity draws it into a collapsing cloud of gas that is destined to become a new solar system. That same atom of oxygen could one day become part of a rocky planet or the atmosphere of a world with conditions ripe for life. This is the ultimate fate of the material we see glowing in the helix today. This cycle of death and rebirth is the engine that drives the chemical evolution of our galaxy. The early universe consisted almost entirely of hydrogen and helium. Every other element on the periodic table, from the carbon in our cells to the iron in our blood and the calcium in our bones, was created inside stars. Elements like oxygen, nitrogen, and neon, which shine so brightly in the Helix Nebula's spectrum, are the specific legacies of stars like its progenitor. Without the violent yet creative deaths of these stars, the universe would be a sterile place, incapable of forming Earth-like planets or the complex chemistry that life requires. The Helix Nebula is a nearby, brilliantly illuminated example of this essential galactic process in action. It shows us that enrichment is not an abstract concept. It is a physical, observable event where a star actively fertilizes its corner of the galaxy with the elements of creation. Therefore, the true oddity is not any single feature, but the breathtaking efficiency of the system as a whole. The bipolar shape ensures that the enriched material is ejected in specific directions, potentially reaching further into space. The Cometary knots act as temporary storage units, protecting fragile molecules until they can be safely released. The complex magnetic fields and shock fronts mix and energize the gas, fostering chemical reactions that would be impossible in a calmer environment. Every component works in concert to ensure that the star's legacy is not lost. When we gaze upon the Helix Nebula, we are witnessing a crucial phase in the life cycle of matter itself. It is a moment of transition where the remains of a past generation are being prepared for the next. This perspective transforms our understanding of our own place in the cosmos. Our solar system, and every one of us, is made from stardust that was recycled in exactly this way. The atoms that constitute our bodies were once inside a star that lived and died long before our sun was born. We are the products of cosmic recycling. The Helix Nebula offers us a glimpse of our own deep history and a preview of our sun's distant future. In about 5 billion years, our sun will undergo a similar transformation, creating its own planetary nebula and returning its enriched material to the galaxy. The beauty of the helix is therefore a humbling and connecting force, a reminder that we are not separate from the universe but an active part of its ongoing, magnificent story of creation and renewal. Our journey through the 40 peculiar wonders of the Helix Nebula reveals a profound truth about the cosmos. What appears as a single, beautiful eye in the sky is in reality a universe in miniature. We have wandered through its chaotic heart, from the searing white dwarf corpse that powers the entire spectacle to the delicate, doomed cometary knots that serve as temporary shelters for the chemistry of life. We have seen how invisible magnetic fields sculpt the gas, how violent shock waves superheat it to millions of degrees, and how ancient light echoes replay the star's final moments across light years of space. Each oddity, from the strangely aligned knots to the tentative whisper of the universe's first molecule, is not an isolated curiosity but a single piece in a grand, interconnected puzzle. The Helix Nebula is a masterclass in astrophysics, demonstrating stellar evolution, fluid dynamics, plasma physics, and complex chemistry, all within one breathtaking celestial object. Yet, for all we have uncovered, the helix retains its deepest secrets. The debate over the central star's potential binary companion remains unresolved. The precise source of the enigmatic X-ray glow is still a topic of intense study. We do not know for certain if the most massive knots will silently evaporate or if they possess the gravitational muscle to collapse into dark, star-forming globules that will carry the star's legacy to new corners of the galaxy. These lingering questions are not a failure of our science but an invitation for the future. The next generation of telescopes, like the James Webb Space Telescope and the upcoming extremely large telescopes on the ground, will peer into the helix's core with unprecedented clarity. They will analyze the chemistry within individual knots, hunt for the faint glow of hidden planets, and perhaps finally capture the spectral signature of that elusive companion star, turning today's mysteries into tomorrow's textbook chapters. This ongoing exploration connects us directly to the universe's great cycle of death and rebirth. The Helix Nebula is a powerful reminder that we are made of stardust, the product of countless such stellar eruptions that have enriched the galaxy over billions of years. The carbon in our cells, the oxygen we breathe, and the iron in our blood were all forged in the hearts of stars that lived and died long before our sun was born. By studying this cosmic tomb and nursery, we are ultimately learning about our own origins and glimpsing the distant future of our own solar system. The story of the Helix is, in a very real sense, our story too. Now we want to hear from you. After this tour of 40 cosmic oddities, which one captured your imagination the most? Was it the defiant survival of molecular hydrogen in a hostile environment, the potential for planet formation within the dying knots, or the ghostly radial alignment that hints at the nebula's violent birth? Share your favorite mystery in the comments below. We love discussing these incredible discoveries with you. If you enjoyed this deep dive into the heart of a cosmic eye, be sure to subscribe and hit the notification bell so you don't miss our next journey to the frontiers of space, where we'll continue to unravel the universe's greatest wonders, one mystery at a time.